Good morning. Good morning, good afternoon, and good evening. Welcome to the final team project presentations of the 2025 Space Studies program. The participants over the past 8 weeks have worked very hard, pouring their energy, their passion, their creativity into this work. This team project that is the capstone of the Space Studies program. They worked very hard together, and here today they will be presenting their ideas to the expert online, friends, colleagues, and those in the room, the Rwandan ambassador, as well as the delegation of Catalonia. And we are excited to see all your wonderful ideas. So with that, I'm going to go ahead and kick it off, as we're running a little behind, to the first team project.
Thank you, Anna. Good morning, everybody. Pleasure seeing you. For those who don't know me, my name is François Spiro. And I must say, to start, that it was a great honor and privilege for me to be the chair of the team project on how to use satellite data for climate change. As we all know, climate change is today a major concern worldwide. Space-based data can and do play a significant role in the adaptation and resilience aspects of climate change. I spent a fantastic time with 37 very talented and friendly individuals with different backgrounds, both in terms of country of origin and education. They worked extremely hard and well, and in a very good team spirit. Congratulations, dear friends. I'm particularly happy to report that some of the key conclusions and recommendations of the team project, which you will hear very soon, will probably be implemented in Rwanda and in Korea. Finally, I would like to thank the excellent lecturers and advisors of the team project, as well as the great teaching associate Ben, of course, the International Space University, and Hanyang University, last but not least. Let's now hear from the participants of the team project the key elements of their work. Thank you.
in 2 minutes.
Sorry, I'm late. I'm here.
Hey, Nick, did you get dressed in the dark?
Damn. I blame the heat, even with all these early warnings. Can't sleep a wink at all.
Yeah. What subject though? One that we're covering today. Where's your tie?
Damn it. Do we have a tie backstage? Oh, thank you very much.
I suppose you've read over your line?
I might be late, but I'm not an amateur, of course.
Good, I never doubted you. 5 in 30 seconds. Are you both ready? And we're live in 3, 2. Good morning, I'm Lauren Taylor.
And I'm Nick Parak, and we're coming here for you from Nova News, live from Ansan. Our first story, a new Korean invention hit the world by storm. An ice cream that does not melt up to 40 degrees Celsius. Dubbed never-ending bingsu, it's become a huge hit with young people and Italians who like to spend most of their time outside in the hot weather. So the next time you're out with your friends and want to enjoy your ice cream for a bit longer, consider getting one at Seoul Station.
Thank you, Nick. Now on to our main story. Global warming isn't slowing down, it's accelerating. Beyond intensifying temperatures and relentless heat waves, we're seeing an increase in flooding, landslides, and climate-induced disasters, especially in vulnerable rural regions. In today's programme, we unpack the science, the global impact, and what's being done to confront this climate crisis.
But before that, the weather forecast with our own weatherman, Shinsuke Kito. Shinsuke, it's all yours.
Thank you, Nick. Let's take a step back and look at the bigger picture, the climate itself. Over the past five decades, the Earth's temperature has been steadily rising. We are witnessing extreme heat events around the world. In 2019, Paris recorded scorching 42.6 degrees Celsius, which was the highest temperature ever. While in Los Angeles, wildfires are getting more common. And in Seoul, as many of you already know too well, the summer in Seoul is so hot, it feels like we are melting. But these record-breaking heat waves are no joke. In fact, according to the data from Korea Meteorological Administration, Seoul's average temperature rose from 10.4 degrees Celsius in 1908 to 14.9 degrees Celsius in 2024. They are driven by urban heat island effects, greenhouse gas emissions, and the acceleration of global warming. Climate change also drives extreme rainfall and flooding. Around the world, from Europe to Asia to Africa, communities are experiencing heavier storms, landslides, and risking the rising flood risks. In Africa, the impact is especially severe. Although the continent sees only 15% of global climate events, it suffers 35% of disaster-related deaths. An extreme example of this is the country of Rwanda, where over the past 5 years, disasters have caused more than 10,000 deaths, 27,000 houses destroyed. They are intensified by urbanization and land development. But Rwanda's story is not isolated. It is a snapshot of what's happening globally. From scorching heat in cities like Paris and Seoul to daily flooding risks in Rwanda, the weather is telling us one clear story. The climate change is here. It affects us all. That's all from me. Back to your hosts.
Thank you, Shin. As we've just heard, the impacts of climate change are becoming more immediate and ever more severe. To help us understand and make sense of these developments and what they mean for our future, we're joined today by a panel of experts on climate science who will help us understand the science, the risks, and the potential solutions. Let's welcome them onto stage.
We're joined today by our panelists, Sarah Jerzik, a leading scientist in atmospheric studies, Yuval Priel, an expert on disaster risk reduction, and Rebecca Caraher, a humanitarian and environmental affairs analyst.
Thank you for joining us today. Our viewers are keen to learn more at the situation at hand. From a global perspective, why are floods and heat waves becoming more intense and severe?
Well, thanks for having us, Lauren. So for most of human history, Earth's climate has actually been relatively stable due to the balance of incoming energy from the sun and heat that's radiated back into space. But unfortunately, human activities have disrupted this balance, and that's what's leading to global warming. So as temperatures continue to rise, the atmosphere actually holds on to more moisture, which causes heavier rainfall and makes heat waves more deadly. So in cities, we call this the urban heat island effect, where heat gets trapped and absorbed, and this is making those heat waves more dangerous. So what might seem like relatively small changes in temperature actually leads to more severe storms, hotter cities, and poses a real risk to people all across the globe.
Yuval, Sarah mentioned global warming, but what is actually happening in our Earth's climate system? Could you explain the science behind this warming a bit more?
But greenhouse gases growth as well. Methane, nitrous oxide, and cool. Hi. Okay, so as Sarah just mentioned, Earth used to be in balance, but greenhouse gases broke this balance. CO2, methane, and nitrous oxides have reached higher levels, which mean they trap more heat. So more heat comes in than it comes out. And this extra heat doesn't just warm the air, it will fuel the hydrological cycle. Actually, for every 1 degree Celsius, the air can hold 7% more water vapor, which in turn can cause more and more extreme events. And while this trend is global, it felt most strongly in climate hotspots. Climate hotspots are regions that are getting warm faster than other areas and are more exposed to extremes. So these aren't just statistics. Those numbers change the way that we feel in our day-to-day lives. And you know, Nick, in fact, 2024 was the hottest year in record, with 1.5 degrees Celsius more before industrial times. So this isn't just symbolic. Crossing these thresholds is meaning that we're entering unknown territory.
Thank you, Yuval. This truly is a concerning trend. Swera, how do we monitor these changes and how do they affect to what happens in urban areas?
Well, Nick, scientists can use satellites to track environmental changes over time. So satellites like Landsat 8 and 9 and Sentinel-3 all host sensors or instruments that can detect infrared light. And these instruments are especially helpful when trying to monitor urban heat islands. And studying urban heat islands is really important because they amplify the global warming effect. So urban areas have less vegetation, more concrete, and overall higher energy uses, which all feed back into the global climate system, which makes rainfall events harder to absorb and cities hotter over time.
Thank you for the insight, Sarah. So beyond floods, Yuval, how does warming actually contribute to landslides themselves?
So when heavy rain falls on already wet ground, the soil gets weaker, which means that slopes can collapse. So if we have two storms together, consecutive to each other, it will be more extreme and even more dangerous. And the question isn't if climate is changing. The question is how well and how fast we can adapt to it. And this is why the landslide risk is going side by side with flood risks.
And when ecosystems lose their natural buffers like wetlands and forests, the situation only gets worse.
Yes, that's the positive feedback loop that we're observing. When there's more heat, it amplifies the atmosphere instability, which in turn can cause more and more extreme events.
Which is why we're not just tracking climate change anymore, we're experiencing its effects in real time.
So the impact is no longer theoretical, it's unfolding across every layer of our environment. Rebecca, Yuval and Sarah have outlined the environmental risks, but what about the people risks? How is this affecting lives around the world?
Well, it matters because these aren't just numbers. These are people's home, safety, and health. Over the past 50 years, climate-related disasters have increased fivefold. So even floods have increased by 134% and increasing. What this means is millions of people are being displaced, losing their jobs, their land, and struggling to rebuild their lives.
This is a worrying and dramatic increase. So when it comes to health specifically, what are we talking about?
So landslides, floods, and heat waves all leave a mark on health. Take landslides, for example. They can cause fatalities like head trauma and internal damage, and sadly, they can often take lives. On top of that, infrastructure damage slows access and emergency response, cutting off your access to medical care. So that means something as simple as going to a clinic can mean life or death. Floods, they can spread waterborne diseases like cholera, respiratory problems, and skin infections. So we're not only looking at the immediate injuries, but the cascade of secondary health problems that exist long after a disaster takes place. And with regards to mental health, the trauma of losing your home, your land, and your loved ones has long-lasting effects.
Yeah. Do these disasters also spill over into the global economy?
Yes, every disaster spills into the global economy. Landslides alone account for 5% of all disaster-related deaths, and this costs us an economic loss of 20 billion per year and growing. And in vulnerable regions like Rwanda, the impact is magnified, where your livelihood is directly dependent upon the land. So this isn't just an environmental issue. This is an economic and social stability issue too.
So the bottom line is climate change is already shaping how people live and survive.
Exactly. We're no longer just forecasting risks, we're living through them. And whether we like it or not, climate change is now a daily human experience, affecting our homes, our jobs, our economies, and our lives.
Thank you. Thank you to all of you, Sarah, Yuval, and Rebecca.
Thank you to our panelists. Next, we move on to a short documentary. The frequency of floods and landslides have been increasing in the global south, especially in East Africa. Rwanda, one of the continent's smallest nations, has been especially hit by climate change-induced disasters, especially over the last decade. Even though there's national policy and international support networks that aim to provide relief, the question still remains, how are the daily lives of average Rwandans affected by this relentless cycle of destruction?
A recent documentary about the impact of flooding and landslides in Rwanda has gone viral, not just for its striking imagery, but for its touching human stories. Over the last 5 years, floods and landslides have upended the lives of more than 52,000 people in Rwanda, and millions more remain vulnerable. Entire villages have been displaced, farmland destroyed, and hundreds of lives tragically lost.
nta kindi kintu na kimwe mfite, nta buriri, nta kintu na kimwe nk'uko mubireba, nuko mpagaze naho kuba ntaho mfite kuko inahangaha nari nahaje kuhashakira imibereho, ariko nta kindi kintu na kimwe ubona nsigaranye ni gutya ameze, nta naho kuba mfite.
These disasters are becoming more frequent and more severe, fueled by the growing pressures of climate change. Behind every number is a family, a livelihood, and a future interrupted.
To truly
A fascinating and touching report.
We interrupt our scheduled segment for a developing story about heat waves. Let's go to Chalisa Gear, live from Seoul.
Thank you, Lauren. Good morning. I'm Chalisa Gear, reporting live from central Seoul, where today's breaking news has spotlighted the alarming rise in urban temperatures due to what scientists call the urban heat island effect, or UHI. With sweltering heat waves intensifying across the city, we're joined by a leading expert to help us unpack what's going on. Joining us now is Professor Epi Kim, Chair of the Department of Global Climate and Environmental Studies at Hanyang Fictional University. Professor, thank you so much for being here.
Thank you, Chalisa. It's a pleasure to speak on this urgent issue.
To start, could you tell us a bit about your background and current work?
my background and current work. Certainly, I specialize in climate adaptation policy and urban resilience with a strong focus on how cities respond to extreme heat and environmental stress. At the Department of Global Climate Environmental Studies at Hanyang University, my team and I analyzed urban heat island effect using a combination of satellite data, local temperature sensors, and GIS based on modeling. In Seoul, we have been tracking the most vulnerable neighborhoods, often those with limited green cover and high surface temperatures, and working with municipal planners to design a data-driven cooling strategies. Our goal is to translate science into practical action for communities most at risk.
Based on the breaking news today, what is happening right now in Seoul?
Right now in Seoul, we are witnessing temperatures in the urban core that are up to 7 Celsius higher than in surrounding rural areas. This is due to the concentration of concrete, asphalt, and limited green space that trap heat. Today's record-setting temperatures in Gangnam and Jongno were not anomalies, they are becoming the new normal.
Is the general population aware of this phenomenon?
General population aware of phenomena, that's a key issue. We recently conducted a survey across 5 districts, and only 38% of the respondents were familiar with the term urban heat island. While many experience that discomfort, they often attribute it solely to climate change, not understanding how city design amplifies it.
And what method did you use to get this data together?
Using the data, we used the mixed method survey, both digital polling and on-the-ground interview. We partnered with local NGOs to reach vulnerable population, including elderly residents who are mostly impacted.
And what message do you think the people need to hear right now?
Message from the right now that UHI is not inevitable. It's influenced by urban planning decisions like reducing green space and building density. Public awareness and engagement are critical if we want to cool our cities and protect health.
Thank you, Professor Kim. That's all from us now. Back to the studio.
Thank you.
Thank you, Chalisa and team. This is definitely some concerning news. I've been told we have some local experts who can provide some more information at the matter at hand.
Let's welcome our team of climate experts onto stage and find out more about the situation.
Thank you for joining us at such short notice. We have Pau Madonio, a technical expert, Elizabeth Hyatt, a satellite remote sensing engineer, and Devin Carrier, a social expert on climate adaptation, all from our very own Hanyang University. Your colleague, Professor Epik Kim, has just told us that concrete in urban spaces can affect the urban temperature. How can you give us a bit more information as to why this is?
So thank you, Nick. Thank you, Lauren, for having me here. So urban heat islands are just a phenomenon why cities and some specific regions of our cities temperature gets significantly increased comparing it to closer rural areas. And this is mainly due to the way we design cities and the way we behave in cities. Among these main factors, we can see that there's surface materials that we use, asphalt, concrete, even dark rooftops. They absorb energy through the entire day, and they don't even have time to release it as intended through night. So this heat stays in the city. Another reason is the urban geometry. If we have narrow streets, if we have very tall buildings, the heat stays inside the city. It creates what it's called heat canyons, and the air is no longer allowed to leave the city. The another factor is the building density. The more density of building we have, the less space we leave for green areas, the less space we leave for parks and for airflow corridors. And this is another important factor. And lastly, we wanted to point out the human factors. This is also important because all the cars we use, all the factories where we work, the ACs that in summer we all love, of course. This also produces a big amount of heat. And in the end, what we end up seeing is that cities itself, they have a microclimate.
Are there any parameters or data that we can use to better quantify and analyze these effects?
Absolutely, Nick. We can use remote sensing tools to measure and analyze the urban heat island effect, and there are a number of indices that allow us to do this. The normalized difference vegetation index is a measure of the amount of vegetation in a region. So the higher the vegetation index, the more greenery there is, and this can help to cool an urban area. In contrast, the normalized difference built-up index is a measure of how many buildings and hard surfaces such as rooftops and concrete there are. The higher the built-up index, the more artificial surfaces, and this can lead to an intensification of the urban heat island. The land surface temperature measures the surface of the Earth, and by combining the land surface temperature with the built-up index and the vegetation index, it allows us to see how green spaces cool and built-up areas lead to an intensification of the heat. So, to summarize, the vegetation index means more greenery and cooler regions. A higher built-up index means more hard surfaces and increased urban heat. And land surface temperature can be used to see this heat distribution.
Thank you both. So Devin, how can these metrics be used by urban planners?
Good question, Lauren. The metrics Elizabeth described show where people are most exposed. But exposure alone doesn't equal vulnerability. To understand who is most at risk, we need to consider sensitivity, such as age or health condition, as well as adaptive capacity, such as access to cooling centers or hospitals. By mapping these social vulnerability metrics, planners can locate not just where the city is hottest, but where solutions will be the most effective.
In your research, you mentioned the restoration of Seoul's Chongricheong River. Pao, how effective has this project been up till now?
So one of the best examples that we have of cities turning into adaptation towards urban heat island problem is, as you mentioned, the restoration of the Chongricheong River. And this took place between 2003 and 2005 in the city of Seoul, that we all are very familiar with already. And as a result, it decreased the temperature close to the river between 3 and 5 degrees compared to other closer areas, which is at least a significant improvement. And this was due to removal of heat-absorbing pavement and the increase of greenery and of greenery areas, and the fact that we were allowing again the air to flow through the city.
And Devin, what did local communities think of this project?
Well, Nick, recently a survey of 86 articles on the river restoration highlighted mixed public response. Some authors suggested that there was positive public engagement, whilst others thought that only an elite few were involved in the decision-making process. All these papers agreed, though, that gentrification was a negative outcome, where rising property values and displacement limited who could benefit from the project. This shows that even well-intentioned projects can lead to social inequality, and we have to have effective policy to avoid this.
Thank you, Pao and Devin. We've just had our breaking news from Seoul. Is this a trend that we're seeing globally?
Absolutely, but it's also important to understand that not all cities behave in the same way regarding urban heat islands. A great example of that is the study comparing London and Seoul, where we can see that the wealthier neighborhoods in London are placed in the southwest of the city. And at the same time, we can see that the SUHI parameter is, which is the urban heat parameter, is way lower. So that means that the wealthier areas of London are being way less affected compared to the poorer neighborhoods. Yeah, that's important to understand. And a reason for that is because wealthier neighborhoods, they have greener areas, they have parks. So yeah.
Could you briefly explain the meaning of the SUHI parameter?
Yes, absolutely, Nick. So all the parameters that I previously mentioned serve as pathways towards the development of the surface urban heat island, or SUHI parameter, as Pal mentioned. Together, these parameters allow us to understand why urban areas experience this effect. And the most reliable way to quantify the SUHI parameter is by comparing urban areas with nearby rural areas that aren't as significantly affected by urbanisation.
And Devin, what is your take? Is this the same for Seoul?
Interestingly, it is not the same. The maps of Seoul show that green spaces and heat are evenly distributed, regardless of income. This difference between cities is important to understand how adaptation unfolds. For example, older neighborhoods on the outskirts of Seoul were left behind during many redevelopment projects, and now they are more vulnerable communities. Similarly, these historical differences are seen internationally. In the US, redlining left Black populated neighborhoods without investment. Now these communities are also left vulnerable to heat waves. This shows that heat vulnerability has no universal solution. Planners need to understand the specific history, culture, and social dynamics in each city to implement effective solutions.
You have shown us some temperature and income distribution maps. Elizabeth, as an expert in remote sensing and satellite technology, could you please explain to us how satellite data can be used to actually monitor the urban heat island effect?
Well, satellites give us the big picture. They allow us to measure the surface temperature, rainfall, vegetation, and land use changes all in real time. And this is data that's almost impossible to collect consistently on the ground, especially in remote regions. If we're able to map precisely cities or larger areas, it allows us to understand how urban areas are changing over time. Smaller regions that can be mapped allow us to follow trends and patterns. And by doing this, we can combine it with the satellite data that allow us to see the multi-layered benefit of all.
So satellite data can create a powerful foundation for strategies to reduce urban heat islands and support climate adaptation?
Absolutely, exactly right. By integrating them into the satellite-based resilience framework, it allows us to cover the whole disaster cycle, all the way from urban heat through to flooding. And this allows us to inform early risk mapping indexes.
Thank you. You mentioned in the study conducted by ISU SSP 2025 participants, and you mentioned that Landsat 8 data was used. Why was this satellite chosen specifically?
So the main reason for us to use the Landsat 8 data, it was to strike a balance between data accessibility and image quality. We tried to use the Korean satellites, the CommSat, which they provide an amazing resolution in terms of revisit time, in terms of spatial resolution. But the hard accessibility that we found when we tried to use this data, and also that we had to purchase the data, so we weren't able to use it. Other options such as Sentinel-2, Sentinel-3 were also taken into account. But same that is happening with the MODIS, another satellite, we decided to go for Landsat since the temperature resolution is, in our opinion, better.
Thank you. Thank you for sharing your expertise. It's clear that urban heat is a challenge both locally and globally. We've heard tonight how climate change is intensifying extreme events and how it impacts people worldwide, and how technology can help us tackle this issue. Elizabeth and her team, to see what this looks like in practice, Elizabeth and her team have put together a short video on how the technology is being applied in the Republic of Korea.
Urban heat islands represent a critical climate challenge in South Korea, where rapid urbanization, dense infrastructure, and limited vegetation have created persistent zones of elevated temperature. In Seoul, temperature can rise up to 4.5 degrees Celsius compared to surrounding areas, implying risks to public health, energy systems, and urban livability. Understanding and mitigating these effects requires reliable monitoring tools capable of capturing temperature variations across both time and space. Satellite data, integrated with ground-based observations, provides a foundation for identifying hotspots, assessing drivers of local warming, and guiding adaptation strategies at the municipal and national levels.
South Korea's monitoring capacity relies on both domestic and international satellites. The Korean multipurpose satellite COMSAT provides high-resolution optical and thermal imagery suitable for neighborhood-scale heat analysis. However, its data is not openly available to researchers, limiting widespread use for climate adaptation studies. For this reason, open access missions such as Landsat play a vital role. Landsat 8, launched in 2013, provides standardized, freely available imagery to track the urban heat island effect, showing how rooftops, asphalt, or green spaces influence city temperature over time.
A focused study of Seoul demonstrates how open access satellite data can be used to track urban heat change over time. Using atmospherically corrected Landsat 8 imagery, land surface temperature was retrieved from thermal infrared data, while vegetation cover, built-up density, and surface reflectivity were quantified using indices such as NDVI, NDBI, and albedo. The analysis compared conditions in the summers of 2014 and 2024. Results revealed that average land surface temperatures increased by nearly 1 degree Celsius, with some districts such as Ganseogu experiencing a rise of up to 3.5 degrees Celsius. Districts with higher vegetation cover consistently recorded lower temperatures, while urban forests and restored waterways such as the Changechong stream reduced local heat by as much as 5 degrees Celsius. By linking thermal indicators with demographic data, the study also identified vulnerable populations most exposed to heat stress, underscoring the importance of combining environmental and social metrics.
4 main recommendations are proposed for South Korea, combining technical, institutional, and social measures to strengthen adaptation and resilience to urban heat islands. The first recommendation is open and integrated access to satellite data. At present, the restricted availability of COMSAT imagery is already
We are sorry for the technical difficulties, but we still thank Elizabeth and her team for showcasing in this video how satellite data can be used to address the urban heat island effect.
Now on to our next segment. We go to our technology correspondent, Bushra Kiani, who is in Rwanda, to present a new and innovative tool that's being used to save lives by giving advanced warning of floods and landslides.
Thank you, Nick and Lauren. Around the world, satellites are being used to prepare for and respond to the impacts of floods and landslides. Earth observation satellites are used for mapping and prediction, telecommunication satellites for emergency communications, and GPS satellites for navigation. Today, I'm in Rwanda with Giovanna Ramirez, lead engineer of the Rwanda project, which is developing an Internet of Things solution deployed across the country to provide an early warning platform. Welcome, Giovanna. Can you explain in simple words what the Rwanda project is?
Of course. First of all, thank you for this space. The Rwanda device is an IoT sensor system monitoring river levels, soil moisture, and slope stability. It sends data via ground and satellite networks to track environmental conditions to provide time alerts.
How is this data collected and used to warn communities?
Well, the data is continually measured from the sensors and combined with satellite radar and optical imagery and precipitation measurements. This data is processed with the hydrological and geotechnical models to predict floods and landslides. The results will feed into the GeoHub platform. It is from the Rwanda Space Agency, creating a dashboard for authorities. And then when the thresholds are exceeded, alerts are sent, allowing communities and officials to act very quickly.
How long will it take to implement the system across the country, and how much area do you think it covers?
Well, the implementation can take between 6 months to 1 year. And we will start in high-risk districts like Route 0 and Gorodero, deploying at least 750 sensors per district, and then we will expand it gradually.
All right. So what's the potential impact of this technology in terms of saving lives?
Well, as you know, our early warning system can protect thousands of people, especially in the rural areas.
So what are the main limitations of the system?
Well, we can think about the coverage, you know, that it needs multiple sensors per area. Also, the sensors require power, maintenance, and protection. And so we can combine solar solution and satellite connectivity to ensure this reliability. And currently, we have prototypes, but the software needs to be developed further.
Okay, thank you, Giovanna. It is wonderful to see such a life-saving device being put into action. Thank you again.
Thank you, Bushra. We now go on to Adam McMillan to hear about a software solution for floods.
Speaking of software, joining us now is David Salmon, Business Development Manager for the Theo HydroWeb software. He's here to share how their software is helping improve flood management. Welcome, David. Can you share us what your tool is and how it's helping with flood management?
Thank you, Adam. HydroWeb is a collaborative project developed by several French space organisations. It uses satellite and telemetry data to provide continuous long-term monitoring of water levels in major lakes and rivers. This allows us to identify areas affected by flooding and give emergency responders the insights they need to plan and coordinate disaster response efforts worldwide.
This sounds like a very promising piece of software. How far in advance can communities expect to receive a warning signal?
At the moment, HydroWeb is updated about a day and a half after new satellite data becomes available, so it doesn't yet provide direct predictions. However, by analysing trends, users can spot areas where water levels are rising and flooding is likely. On a national scale, this makes it possible to focus flood mitigation efforts on the regions most at risk.
So what are the limitations and what are the future directions for this software?
Currently, we are limited by the spatial and temporal resolution of the satellites that provide the data. So, we look forward to integrating future altimetry satellites. We are also working on predictive models to identify flood risks before they happen. One of the most challenging things about flood and landslide mapping is that any models implemented need to be specific to the region being studied. For this reason, there are future projects creating models optimized to the unique geographical and hydrological conditions in Rwanda.
Thank you, David. We look forward to the development of this software.
It's encouraging to see all these innovations from the space industry.
Definitely. Now we're honoured to welcome a distinguished panel onto the stage from the Rwanda Space Agency. First, we have George Kazera, our Chief Technology Officer, Sepa Friesen, our Director of Outreach, and Pearly Pandya, our Vice President of Commercialization. Welcome.
We're delighted to have the CTO of the Rwanda Space Agency here with us today. George, could you tell us a bit, what are the biggest priorities at the RSA currently, and how are you progressing in the development of disaster management tools?
Thank you, Nick. Thank you, Nick, for having me. Rwanda Space Agency, we have invested in establishing a geospatial hub. This is a centralized platform that is used to process and analyze satellite images, but also other geotagged data. And using artificial intelligence, we support with information different critical sectors of the country. Of course, the disaster management. Our engineers, they are building different models where they combine satellite images, but also other data such as topographic data. They use climate data, and with that, they map out flooding and landslide hotspots and provide those information to our stakeholders who are involved in the disaster management. And that is all phases, be it prevention, be it preparedness, response, and recovery.
Thank you, George. And does the Rwanda Space Agency have any plans for the future?
Yeah, of course. Now we are currently busy trying to improve our models. We want to make them more accurate. We are extending the deployment of sensors, and also we want to ensure that we continue to acquire even different type of data beyond just the standard satellite images. We want to have more higher resolution images, SAR images, hyperspectral, LiDAR, and so on. But again, the main focus is really to ensure that our early warning system is much more accurate.
Thank you, George. That's some really exciting news. And Sepe, our expert in community and ecosystem management, how do you involve the different stakeholders in the implementation of your technologies in disaster management?
Well, to echo George, thanks for having us here today. The Rwanda Space Agency wants to focus its community outreach efforts into two different objectives. The first objective is to basically make the next generation excited about space. We want to focus on space education, and we want to continuously grow our presence in Rwandan schools. Further, we also want to make them excited about solving the national issues using space technology, and we want to convince them to pursue a career path in STEM. Secondly, we want to educate the local governments and communities. We plan on using the already in use community workers in the healthcare system, and we want to train them to be able to work with our latest platforms. And using these community health workers, we can actually earn the trust of sometimes quite remote communities. And by doing that, we can get evacuation signals to them as fast as possible. And by doing that, the Rwanda Space Agency can actually provide a crucial way, a crucial link between the central government, NGOs, local governments, and most importantly, the communities.
Thank you, Sepe. And Pearly, as the Vice President of Commercialization, what are some of the big initiatives currently that you're most excited about to build Rwanda's disaster management capacity?
Well, thank you for having us here at NOVA. When we think about Rwanda's space priorities, I think three areas really stand out. The first is regional cooperation. So we're working with the African Space Agency focusing on workforce development, to echo Sepe, to make sure that our young scientists and engineers are equipped with the skills to leverage space for challenges like floods and disaster managing. Second is international cooperation. At the Rwanda Space Agency, we're really proud of our global partnerships to advance technology transfer. This can be done through multilateral funds or shared payloads. And this is important to sustainably build capacity, but also build real resilience. And third, finally, probably my favorite, is commercialization. I'm really excited that we're partnering with organizations like the IREAM Invest facility, unlocking investment into the private sector in Rwanda, so enabling startups and private projects like the Karinda project that are already delivering innovative solutions. So really, these three efforts together help Rwanda use space to be best prepared for the future.
Thank you, Pearly. And just fresh off the press, I hear that ISU SSP25 have recently published a report with the recommendations for the use of space technologies in the context of climate change. In this report, it includes a roadmap with some initiatives for short, medium, and long-term initiatives for enhancing access to satellite-based solutions for disaster management in Rwanda in particular. What's your take on the recommendations, and do you think they're implementable?
Yeah, thank you, Rorin. Let me first thank these brilliant students of ISU, SSP25. At the Rwanda Space Agency, we want to build technology that impact people, that contribute to the economy of the country. And that can only be achieved if we take into consideration the whole ecosystem, triple helix, the academia, but also the private sector. We also continue to ensure that the government is equipped with the right tools, and in this particular case, to ensure that we facilitate in the disaster management. So clearly, these recommendations align daily with our priorities. Let me explain that. the first recommendation in short term, this is really to ensure that we have a quick access to different data that we need for building our models, and without necessarily having to build our own satellite. So this will help Rwanda Space Agency to continue mapping around these flooding hotspots and landslide without necessarily having satellite in the space. Now, on short term, there's a recommendation to ensure that we have collaborative initiatives with other countries and also other commercial companies to co-launch payloads. Rwanda can, for example, launch a secondary payload to another main mission of another country. And we continue building the capacity of our people. But long term, we can take advantage of a different regional organization that Rwanda is part of, such as Smart Africa Alliance, East African Community, and others, and pull our resources together and be able to build an Earth observation constellation that can help us to have sustainable access to this type of data that we need without necessarily having to invest a lot, but we share the costs. So overall, I believe these recommendations are implementable, and really looking forward to borrow some of this recommendation and put forward our space ecosystem.
Wow, these ISU students truly sound brilliant. Thank you very much, George, Sepe, and Pearlie, for explaining more about the Rwanda Space Agency.
That's all from us today, here live from Ansan. We hope the news has been informative and insightful, highlighting the global issue of climate change and how it's affecting everyone across the globe. A special thanks for all of our guests on joining us and by sharing their experience and expertise.
We hope to see these recommendations and solutions be implemented and have a positive effect on our climate change.
I'm Lauren Taylor.
And I'm Nick Parak, signing off from Nova News.
Go live in 2 minutes.
Sorry, I'm late. I'm here.
You think something would change in 10 years of doing this? I'm not going to mention the graying hair.
Sorry. Oh, you know me too well. Thank you very much, Lauren. I actually did not have the time to look through your sections. Could you give me a quick summary, please?
You can, yes. You might want to dust off your face slightly as well. But of course, we are talking about the Department of Global Climate Environmental Studies here at Hanyang University. Has launched a spin-off together with Elizabeth Hyatt. Do you remember her from 10 years ago in 2025?
Yeah.
Well, basically, they've created a satellite solutions that combine different disaster indices together, and they map them across the globe. They've already mapped South Korea, UK, Brazil, and Rwanda, and they implement local data. It's expected to dramatically improve disaster resilience.
That actually reminds me of the Corinda project. That's on my section. That's been going strong for a couple of years now. They've already implemented over 15,000 ground sensors in high-risk areas in Rwanda. That's about 2/3 of the country already covered. And since landslides happen so frequently, they've already been put to the test countless of times. And they've been able to alert the population early enough so they can relocate safely, saving thousands of lives already. They're planning on even expanding into Tanzania and Indonesia as well.
Wow, that sounds really good. And lastly, we've got the South Korea section. So they started launching their own satellite constellations with their own Korean-made rockets. And they've been working on them for quite a while now. And they'll be using them for monitoring urban heat islands. So they'll be able to identify urban heat islands with around 95% accuracy, which is a dramatic increase. They've been talking about some policy integration, but it's still early days, so we expect to know more maybe in the future.
Lights, please. Are you both ready? And we're live in 3, 2.
Good morning, I'm Lauren Taylor.
And I'm Nick Parag. We're coming here live from Ansan with Nova News. Today's segment is special on climate change. Have you noticed the recent decreases in global average temperatures and the shift in flooding patterns? Have we finally been able to close in on a viable solution for climate change?
Today, we'll dive into the biggest headlines and take a look at how far we've come. Stay tuned for our special segment on One Planet, One Problem. Thank you ever so much for listening to us. Do you have any questions?
Don't be shy.
Any questions? Yeah.
Thank you very much. Great presentation. Somebody has to have the first question, so up to me. Can you please tell us what are the key factors related to climate change and especially how these factors apply to Rwanda and to Korea?
Okay. Well, so a lot of key factors, as we said, like include greenhouse gases, and the connection that we saw between Rwanda and Korea are the fact that they are both hotspots in different ways. Rwanda is a hotspot because it's more vulnerable to extreme events, just like landslides and flood. And as we mentioned, in Korea, it's hotspot because it gets warmer than other areas due to the urban heat effect. And you know, when we speak about global warming, this is the trigger, but it actually, the question is how it multiplies risks across different systems, earth, land, and air.
And to complement Yuval's answer, when we were doing our research, we were also looking into effects such as the radiative heat transfer and the albedo effects, which we see in their sort of more major contributions to urban heat island and the urban heat island effect, where as sort of Pao discussed and the expert panel we had, where there's surfaces that don't reflect but absorb and then retain heat, and also other initiatives such as sort of human factors that lead into kind of this global warming effect.
Yeah, thank you for your presentation. I was wondering for the satellites, did you consider other perhaps commercial providers of satellites? And
Yes, we did. but the budget is also the budget. So we ended up also using Landsat 8 because it was aligned with the methodology that we wanted to follow. It's great to have NDVI images. It's great to have NDVI images. It's also nice to have land surface, temperature, and other figures that you can get from these parameters. And another important factor was that we wanted to use the same data because we compared 2014 with 2024. And Landsat 8 has been in orbit since 2013, sorry. I think it has been commented already in the presentation. And we wanted to use the same data for both years, for 2013, 2014 and 2024. So that's why we went for Landsat 8.
So that was a lot of information, and thank you. It helped me understand a little bit more about climate change. Can you go through again, what would be the first step towards implementation with a potential client and user here?
Yeah, so I'll start with the South Korea side, and then George will take on the Rwandan side. So I think first, open access to data was found to be common on both sides, and that is really something that allowing scientists to have with free access without restriction was probably our short-term solution on both ends. And then capacity building is another theme that was super common. We ultimately suggested on both of our case studies that domestically, both space programs should have an entire Earth monitoring constellation in the long term as well.
Yeah, so thank you for the case of Rwanda. More importantly, is really to start working toward improvement of already what we have in terms of our warning system. And that is possible if we continue to acquire different type of data. So initially, of course, we cannot just go into launching satellite, but you can start accessing some of affordable data that and high resolution data that exists on the market. We have some example companies like Planet that have more frequent data captured over the territory of Rwanda. And of course, continue toward building national capabilities. But now, in the short term, something that was mentioned here, maybe we want to emphasize, is these solutions cannot be, you cannot come with a technology solution if you don't take into account the communities. It is very important that whatever we develop in terms of technology is adopted by, first of all, stakeholders, the team that intervenes in terms of disaster management, but also the local communities themselves. So we want to go down to local government, district levels, and so on, give them those tools, train them how to use them, and really inspire them to trust technology, because the trust is a very big barrier in any implementation of any technology. And once they have it, we continue working on the improvement and so on, and we believe we'll be able to mitigate these the consequences of these disasters. Yes, of course, there's a number of things that we're learning from already what Korea is implementing. They are really more advanced in terms of satellite assets that they have, and also even some good models. There's a lot of lessons that we learn from the research done by on Korea. We believe actually beyond just focusing on what we are doing, international cooperation is very key. So we intend to continue working with some countries like Korea and others that have advanced a little bit, borrow that knowledge and implement it in different contexts. And I believe also Korea also has learned a number of things on Rwanda side.
Yeah, so Korea recently, well, I should say relatively recently, has shifted from a foreign aid receiving country, and it's really quick economic growth. It's now a foreign aid giving country. And we actually found in our research, there's an existing partnership on the educational side between South Korea and Rwanda to share this information.
A bit more on the project management side of the report, actually, of the TP. It is on. Oh, close, I'm sorry. A bit more on the actual process of how we did our report. It was, so we were separated in 2 case studies. One was based on flooding and landslides with a focus on Rwanda. The other was urban heat island effect with a focus on Seoul. And we worked for kind of the first half of the TP. We worked separately on our case studies. And then the idea was from the get-go that the connection between the 2 of them is the hydrological cycle. So the heat that is generated in Seoul and in Korea is what also fuels higher evaporation rates. These higher evaporation rates cause more intense rainfall. In this case, it doesn't directly link to Rwanda because Rwanda's weather comes more from the west side of Africa, from the Atlantic Ocean. However, the idea was to connect them through this. Korea lent itself quite well as we're here as one of our case studies. And in the end, for the recommendations part and also a bit for the technical discussion, we joined up together again and discussed, so what are some of the things that connected to even now already, maybe policy-wise, which then we found out is already implemented as well, and how we can connect them further as well.
And just to add a brief comment there, this summer we've all been here and we knew that during a week it didn't stop raining. We had also flood problems, not here, but in some regions of South Korea. And we're pretty sure that some of the ideas and the recommendations that we gave to Rwanda, that also some of them could be applied here in South Korea, not only here, but all over the world.
Does anyone online have any questions? Rodrigo?
Hi, hello, good morning. So first of all, congratulations for the team project. I enjoyed very much the presentation. I think you did a very nice balance between a more lively content and going very deep technically. I enjoyed it very much. I have one question is to, could you comment a little bit more on the role of AI in the both use cases of Rwanda and Seoul?
So AI is very critical. First of all, just to put in the context, over the last maybe 2 decades, the world was really focusing on taking satellite images and so on. Actually, we have more than actually we need, but they were not used. Why? Because we did not have the capability we have today with the advance of the AI and also, of course, the processing machines. Thank you. Now with the AI capabilities that we have, we use some techniques of AI like machine learning and deep learning. So we train our models to recognize certain features. For example, the case of landslides. So we teach the machines or the models the different features that could produce potential landslide. Same for floodings. And when you take a satellite photo and you have been teaching that model how to recognize water, different features and topography, it becomes so easy in the processing. And actually, when you even add more information like climate information and so on, you're able actually to predict in the future a potential or likelihood to have a landslide or a flooding. Same for also the Korean case. We did it, deep learning and machine learning are very critical in order to process such images in the shortest time and be able to assimilate this significant amount of data in a very short time.
And so what George is referring to is more like ground processing of AI, right? We're using imagery, but on the South Korea case study side, we also researched and explored onboard uses of AI and ML. So we're talking about, let's see, autonomous responses to anomaly detection and things like that. Like he mentioned, there's a lot of complications with an enormous amount of data. That means you need higher processing power, more storage, more power, better thermal systems. So it complicates things quite a bit. But I think more significantly, one of our major recommendations in the short term, so we'll call that 0 to 2 years, I believe, out of the South Korea side, was the recommendation to create an urban heat island digital twin of Seoul, so that we can take the time in the long term to train that and see the effects of different variables there. I saw a hand from Juan online.
Yes, hello. I hope you can hear me well.
Good.
Hello. Thank you for the opportunity of being with you from Barcelona. As you know, in the Iberian Peninsula, there are also heat islands, and even worse, there are many bushfires this year, and also landslides. So we're very interested in what you have done. Impressed by especially the depth of the research you've done that we can see in your report. I was impressed by the literature search, and I can see some heads nodding here among my colleagues. Congratulations for that. And we know that we always ask for more than what you can do. But I'm sure that in your research, you must have come across some ideas on the business side of things that obviously did not make it into your presentation or your report. But could you share some ideas on, first, the economics of the effects of climate change, if you have them with you, or if you could mention some sources where you think you would look for them, the economic impact, but also business opportunities. The solutions and the recommendations you have made are, I believe, addressing mostly public agencies. But have you discussed or come across any ideas for new businesses that private entities could tackle to offer better services and to help with the extreme weather effects or warnings, etc. So over to you. Thank you very much.
Thank you for your question. To answer your last question first, for example, the Corinda project that we suggested here, I know it wasn't super clear, but that can be implemented via policy, via government, but it can also be a private entity, and that was the original idea going forward. But then in alignment with all of our other recommendations, we recommended it to the government. But any startup, any business can invent, and that was with the idea of these remote sensors that can be implemented across business and entrepreneurship as well. For many of the recommendations that we have via even the community education that George was alluding to, that can also be an entrepreneurship opportunity for anyone who feels, I'm only talking about Rwanda right now because that's the one I was part of, but any individual who feels that they have any expertise and wanted to make an impact in their communities, like entrepreneurship can help with that. You could start your own educational workshops, you could work with the government, you could work as a private entity, and that's just coming off the top of my head. As for, we do have a lot of economic impacts with regards to global warming and climate change, though there's quite a lot of facts to remember off the top of my head. For example, in the World Bank, we mentioned a lot of that in our report, and also with the World Health Organization, landslides cost around 20 billion per year. And that's just landslides, that's not floods. So if you were to add floods into that, it costs over 200 million per year, and only in the African region. So when we combine the world, this is quite an expensive problem that we have. So that's what we meant by saying that it's not just an environmental issue, that it actually impacts us wholeheartedly. So yeah, I think Pearlie would like to.
On the South Korea side, less on the economics and more on the business opportunities. There's definitely some synergies with what we saw in a lot of our sections. So there's room for mostly public-private partnerships. So as you know, a lot of this money comes from the government, but bringing the private entities in allows for more, I should say, accelerated development. So we're talking about, I should say, AI applications of managing the imagery that comes down and training those models, of course, but really predictive measures is what we're looking for there. And we think that public-private partnerships is the way to go there.
Just last point on what Rebecca said as well, for Rwanda, just to kind of emphasize a bit more as well how much of an economic impact this is. About 25 to 30% of Rwanda's GDP comes from agriculture, from the agricultural sector, and landslides and floodings both increasingly affect those, like the land, so the agricultural land. And that is a huge problem, not only when we talk about usually about agriculture, it's more on, okay, food scarcity, which is a huge problem, but in this case, it's also a large economic factor. I think about some of the sources that we've included in the report also talked about 60% of Rwandans are employed in the agricultural sector. So that's so many jobs being affected by that and the whole economy of the country as well. So that is something that needs to be, like, the losses are immense in that part.
Remco has a question online.
Thank you very much.
Yes, well, first of all, assuming you can hear me, congratulations on a job well done. I read your report with much interest, and this is a very urgent issue, of course. Now, based on work that I've done in the past in Earth observation, one of the key issues why Earth observation solutions don't always work, especially in disaster recovery situations, is timing. And you said yourself that some of the satellite data that is available after a day or a day and a half, which for disasters is often too late. The reason for that, apart from technical issues on the satellite side, is often the uptake of the data. So the usage of the data or the flow of the data from space to the people on the ground who actually need it, very literally, the fire brigade, the instances that are on the ground and that can provide support. How do you overcome the issue of getting the data to the right people immediately without delay?
So, aligning with what we were just discussing, AI models play a very important role there. Of course, the more satellites we have and the faster the temporal resolution it is, the better, of course. But as you mentioned, like, for example, with Landsat, it was 16 days revisit time. That's why satellites are a key aspect and a key tool there in the imagery, but also in terms of letting the population know that they are in danger, making them be aware that they have to act. It's also responsibility of the ground stations, of the ground devices. And I think the combination of both is what leads to faster responses, even if the imagery of the data itself, it's not instantaneously recorded.
Maybe just compliment, maybe from the experience. We had a disaster flooding in May 2023. And of course, the access to satellite data was very critical and real time. We had to also trigger the disaster, UN disaster charter. And this disaster charter will allow any satellite flying over your region to immediately take images and avail them free of charge. That was very key because we're able to access almost live images, and we're able to follow the progress of the damages almost every few hours, and we're able to help the team that was on field in time. But beyond that, we also see an improvement of more constellation coming up. As I mentioned, the case of Planet that has now a very high visit time, and we see more coming up, which we believe is going to really help to have timely access to data. And of course, it said more ground stations need to be there to be able to download those data on time.
And maybe to finalize that, I think there's also definitely an interesting case in using predictive weather forecasting. We've now seen that there's a couple of startups that are now doing such a good job using AI in weather forecasting that they have an immense bargaining power there. So there's definitely a need for a little bit more competition on that side because they're doing too good of a job, but that is at the same time a very good thing to look forward to in the future.
Excellent, thank you.
All right, if there aren't any more questions before we close, we'd like to invite the rest of our team to join us up here, please.
So let's sit here. So on behalf of this excellent team, I hope you enjoyed this presentation and the Q&A session after that. And as I said in my introductory remarks, this was not only a great academic work, and we really hope that some of the recommendations and conclusions will be implemented, particularly Mr. Ambassador in Rwanda. So thank you very much for listening, and all the best for everybody.
We're going to stay up here for one quick photo with the ambassador and the team and the chair.
Amazing. It's like one of these boots. It's like 20 years.
Very good, very good, very good, very good. Very good, everybody.
Thank you, Sandra.
All right. Hello, hello. 안녕하세요. So I am the TP chair for AI on behalf of the team and also our TA, Carol Danguas. Thank you for actually being here online and in person. So AI, artificial intelligence, I mean, it's been around for decades, but it's only in the past few years that we're really feeling it by ourselves as well in our daily lives. So in terms of the space industry as well, so it's now also leveraging AI technologies to benefit the space industry. So it's why this summer, this particular TP and team are focusing on AI applications for space exploration beyond low Earth orbit, and specifically on predictive maintenance, not just for spacecraft, but also for spacewalkers. So just to also point out and to acknowledge that this team is really diverse. I mean, it's they've come up with a very comprehensive and deep report that we're really proud of. But at the same time, they actually went further. They managed to develop two basically developed working models for their AI models. And I think in terms of ISU's history, that's actually unprecedented. So thank you to the team. And so without further ado, this is TPAI.
All right. Hi, everyone. Good morning. How are we doing? Welcome to the second presentation of the day. We're going to be focusing on artificial intelligence for space exploration. So what we did is we looked at the role of AI in real-time decision-making for space exploration. And as she mentioned, we had a very diverse group. We had 42 students from 28 different countries in the group. And we have all of our pictures up here. We had our great chair, Emmeline, and our TA, Carol, to assist us along the journey. So that was really great. And we're going to be discussing what we've been doing for the past 8 weeks in the following slideshow. So with that, I'm going to go ahead and play an overview video we made. So I hope you enjoy, and we're going to turn the lights off for this.
Are based on two different strategies.
The first one is on schedule, so planned maintenance, and the second one on failure, so we react when fault happens. Well, this strategy can work for the ISS because we're close to the Earth. It is harder to take it for future exploration missions, as they will be very far away from our planet, and communication will take longer, as well as operations will become more complex. That's why we need to automate maintenance, and for the EPS, maintenance is not enough. As you see, many systems rely on it, so if it fails, don't take a holistic approach. That's why we didn't stay on the technical side of things, but we also took 3 other points of view: environmental, economic, and legal. So to move on, we'll start with the EPS system and its 3 subsystems. You can see here on the slide power generation, power storage, and power distribution. To start with, on top left of your slide, power generation. Basically what it does, it converts sunlight into electricity through photovoltaic arrays, these elements over here. Before we move into the main failures, we must take into account that the EPS on the ISS is mounted outside, so it is exposed to the space environment. Here we have phenomena like radiation, solar wind, coronal mass ejections, cosmic rays, and high extreme temperatures. So that's why the main failure points for this part of the EPS relate to mechanical degradation due to this exposure. Maintenance is done through EVAs on 2 different strategies mentioned before, on schedule or on failure. So we react when failure happens. The data that we're interested in collecting here relates to voltage and intensity, current, as well as in temperature, because we want to make sure that the electricity that is generated goes through our system properly. Moving on to the second part is power distribution. Basically, it routes power from the batteries and the solar array to the entire spacecraft. Here, main failure points relate to electronic faults, overcurrent events, as well as thermal issues related to the same problem as before, the EPS being mounted outside of the ISS. Maintenance here is reactive and corrective. What does that mean? Basically, we just react when failure happens and we change the entire subsystem for a new one. Data here is also related to voltage and current, as well as temperature, to make sure that the energy is distributed correctly within the spacecraft. Last but not least, the power storage. It's this part here, the batteries. Basically what they do is they store electrical energy from the power generation subsystem to supply it to the spacecraft through the power distribution when the power generation cannot meet demand. When does that happen? For example, with events like eclipses, when the solar arrays cannot generate electricity. So here we've got 2 main failure points. The first one related to power anomalies, so overcharge of the battery, over discharge, as well as short circuits. And the problem that relates to the ISS, which is called cycle-related power capacity fade. What does that mean? Basically, the ISS orbits the Earth every 90 minutes. This means 16 day-night cycles every 24 hours. A day-night cycle is equivalent to a charge and discharge cycle. So if you add up all these charge and discharge cycles over time, those are a lot. Many of them over time, meaning that the batteries degrade and lose capacity. This is a problem that applies to the ISS, but we need to take into account here that maybe for future space exploration missions, it's not applicable. So maintenance is done through telemetry trending to make sure that the batteries charge and discharge properly, as well as on EVAs to substitute them or change them when they don't work anymore. Data that we collect here relates to current and voltage again, temperature, and also internal gas pressure to make sure that the batteries do not overheat and do not have the risk to explode. So once we have collected all this data, we can create an AI model, and that's what we did. I will now hand over to Suhail to tell you more about it.
So thank you very much for the introduction, Albert. So now that we have a general idea of the EPS, I want to come back to our research question. How can we use AI to support predictive maintenance in the EPS of a space station? Well, first and foremost, we need to collect and utilize data. And this is actually not that trivial. So we have identified a challenge in the availability of data that we can get from actual space stations, which is why we went for the next best representative data set, which was data coming from a custom-built battery testbed from NASA Ames. And we looked at 22 lithium-ion battery cells and essentially 3 profiles, namely the charge profile, the discharge profile, and the impedance profile. But before going into the data set, you realize we actually only focused on a unit of the EPS, namely the power storage unit. And this was done because we had the available data. So we used the power storage unit as a proof of concept, but this can also be performed on the other units, namely power generation and power distribution, and even beyond that for other subsystems in space stations. And how can this be done? Well, we have to look at features, parameters, and for the power storage, we looked at voltage, current, temperature, resistance, and capacity, and we plotted that data to see how it actually looks like. On the right, you can see capacity degrading over discharge cycles, which essentially could lead to faults. And ideally, these are faults that we want to predict, and even the moment before these faults in order to perform predictive maintenance. But before doing that, yes, data was available, but it was nested, unstructured, and we had to do a lot of data processing before that. So we grouped our data into several data frames, into the charge cycle data frame, discharge cycle data frame, and impedance cycle data frame. And what we've done is we've actually implemented an isolation forest algorithm to identify anomalies. And what we've seen is that anomalies were fairly sparse in the actual data. So what we did is we synthetically injected anomalies to simulate conditions like overvoltage, undervoltage, overcurrent, undercurrent, and high temperature in order to train our models. And then we classified the data. And this is actually quite important. So from right to left, we've classified the data into 3 different states. The green box here shows the nominal state or the normal state, which means nominal operation of the batteries. We have the fault state over here in red, which actually means that anomalies persist over a certain amount of time, which would mean a failure. And then we have our most important state, which is the pre-fault state, which is the state just before a fault state. And ideally, this is what we want to predict. What we then see is an imbalance in the data set. You see that we have a lot of normal states, which should be the case because it means nominal behavior. But for training, this might become actually an issue, which is why we used an oversampling technique to balance out the data set to improve classifying the pre-fault state. And then we're ready to model to train our models. So we looked at several models Two of them are tree-based, which is Random Forest and XGBoost. They were included because due to their simplicity, but also because they handle high-dimensional data very well. One takeaway message for these models is actually that you can see on the right here, we actually plotted their feature importance, and you see that XGBoost actually considers way more features than Random Forest, which actually will show in the results later. We've also considered two deep learning models, namely long short-term memory, LSTM, and temporal convolutional network, TCN, because they capture temporal dependencies very well, and they also handle variable length sequences. We've plotted their training loss and validation loss, and what we see is that TCN was actually better in terms of that because it has less loss. Once you train your model, you need to evaluate it. We used common AI performance metrics, namely recall, precision, the F1 score, and the accuracy. And priority was given to the recall because it's crucial for safety as it identifies missed anomalies, which is very crucial for safety critical systems. And we started evaluating our models. Random Forest, which had a high recall but a moderate precision, was very good, but it also means that we have many false alarms. For LSTM, we had the complete opposite, a moderate recall, but also high precision, which essentially meant that we missed many warnings. And then we have TCN, which was very good in terms of recall, but it has low precision, meaning that we had excessive amounts of false alarms. And finally, our winner, XGBoost, which had a high recall, high precision, and it was well balanced out overall, the performance metrics. And with that, we have decided that XGBoost was actually the model to be used for predictive maintenance in the EPS of a spacecraft. And of course, there are always future considerations. You can always improve your solutions. What we want to do is we want to look at data diversity. We want to have more real-world data on pre-fault and fault cycles. Remember when I said we couldn't get data for space stations? This is what we want to do. We also want to refine our future selection to improve generalization and use or make use of deep learning models to combine it with our XGBoost in order to perform a bit better. And finally, we want to deploy our actual model to test it in the real world. And with that, we have a proof of concept for our product out of which we can actually create a business. And I'm going to hand it to Raf, who will tell you more about that.
Thank you. All right, so with an AI model now trained, we have a key question to answer, and that is, does a market exist for predictive maintenance currently? So in order to answer this question, we first wanted to look out into other sectors on Earth specifically to see how predictive maintenance has been applied in the past. So in 2024, the global predictive maintenance sector was valued at $10.6 billion, and that is projected to grow to $48 billion by 2029, representing a 35% compound annual growth rate. That is significant over 5 years, just reflecting the advances in AI that are to come. Now, zooming in a little bit more, a report in 2024 by Deloitte looked at the implementation of predictive maintenance into solar farms on Earth. Now, post-implementation, predictive maintenance lowered maintenance costs for solar farms by 70%, and also equated to about that same decrease in maintenance costs, in maintenance costs. And so with that question being answered, it's easy to say that predictive maintenance can lower costs, but what exactly does that mean? So we identified 3 key sources of savings. The first being anticipation in manufacturing. So if you know a year ahead of time that a part is going to break rather than a week or a couple of days, you can get a supply chain in order to get that part produced at a much lower cost than what it would cost if you're scrambling. Secondly, reduce downtime. That same Deloitte report identified that downtime can reduce by 35 to 45%, meaning higher operational efficiency, parts working better, and more revenue coming from your company. Finally, we wanted to look at human maintenance. So if you're considering that a part breaks down, but you know what part is breaking, you can directly target that what you want to repair rather than spending time troubleshooting and finding exactly where the issue is. This is crucial for implementation of predictive maintenance in a spacecraft. And so with that, let's look into the space sector and see, is there a market for this right now? So in order to answer this question, we wanted to project what a market would look like. Now, the ISS is set to be decommissioned in the next 5 to 10 years. And so we wanted to build our market based off of private space stations that are going to be coming in the next 10 years or so. And so in order to answer this question, we found an expert interview mentioning the operational cost of space stations, and our projection with 5 private space stations to be launched or developed, we identified about a $2.2 billion US market that will exist by 2035. Now, if that's the operational costs that are going to be going up, what exactly would be spent on maintenance that predictive maintenance can help with? So to answer this question, over the last 25 years, we use the ISS as a proxy to see exactly how much of their operational costs have gone into maintenance. Now, operational costs being defined as launch costs, development of cargo resupply, and also maintenance. About 37% of that went directly into maintenance, meaning EVAs, putting the parts back onto the station. And so using that, we identified about a $790 million market for operational costs. Now, from that market of maintenance costs, what can predictive maintenance help with? So in order to answer that, what we did was, as Albert identified, the key points that, or the most probable failure points on the space station, we wanted to predict how much of that can predictive maintenance prevent and predict before they break. And so we identified about 55% of the most common failure points would be able to be predicted before they are breaking. And so that leads to about a $434 million market that can be saved by predictive maintenance. And so with a market opportunity existing, we want to know what is the legal aspect of everything. And so with that, I'll pass it over to Joanne to answer that.
Thank you, Raf. Having discussed the financial aspects, let's look at the legal aspects. Is this possible? What do we need to focus on? So in terms of the legal regime, we're going to discuss 3 main topics and revolve around it in this entire presentation. That's risk, liability, and responsibility. To this end, we're going to look at the space law and how it interacts with the AI regulatory regime, focusing one on the Outer Space Treaty and in particular, state responsibility, liability, and supervision, noting that it also allows for space exploration to be done in accordance with international law. There's the Liability Convention, to which it talks about absolute liability and fault-based liability. And there's Registration Convention as well, looking at who put what, where, and when. With the AI regulatory regime, we don't have an international standard on the same, but there are multiple efforts in different regions on this, as highlighted on the screen above you, all of which talk about the following key principles. 1, risk management. 2, responsibility and liability, continuous supervision, safety conscious, and confidentiality of the data. So what happens when an AI system makes a mistake? Who's at fault? Consider this example. If country A, say, had an AI system that failed to detect degradation of their solar array, leading to loss of power, and this affected country B's left support system, which is the partner module. At the same time, country B and country C were collaborating on an effort, and the effect in their system damaged and compromised the collaboration between B and C, leading to an astronaut in country C being injured. Who's at fault? Is it country B? Is it country A, where the fault originally lied? Let's add a layer of complexity. Say that the AI system was purchased from country D. Do we look at the manufacturer? How do you handle these issues? So while discussing liability is a complex topic, and we're not going to go into that right now, we want to ascertain the aspect of responsibility and also continuous supervision. How do you look at a system which you don't fully understand? To which end, we're going to look at the AI decision-making. So the first aspect, there is human in loop. Human in loop basically means before an AI system implements a decision, it needs to be authorized and expressly authorized by a human being. Given our example above, basically it would make liability easier because someone was involved, someone agreed, someone approved. Second aspect, human in loop, basically meaning a human being was notified of the intended decision. It doesn't need the authorization, but there was notification prior, making liability a lot easier as well because there was prior notification before the decision was made. Then there's the aspect of fully autonomous, in which end the AI system makes split-second decisions without necessarily having prior consulted a human being. How do states handle this? How do you go about it? Which leads to the question, do you trust the AI decision? considering AI is treated as a black box, basically meaning it looks at the data it's been fed and comes up with the best possible outcome, which you and I as a normal human being may not necessarily understand the thinking process. How do you supervise a system that you don't fully understand their thinking process? To this end, we determined that we need to look at fairness, transparency, and explainability in all our systems. Basically, coming back to the aspect of continuous supervision and due regard on the Outer Space Treaty, and overall the principle of liability, because at the end of the day, it is fault-based liability. So how do we handle this? How do you best tackle such issues that are currently existing? One, as we earlier mentioned, risk management. This is very critical in everything that we do. Risk management looks at safety by design, privacy by design, and ensuring there is minimal damage and loss to human life, while also encouraging innovation in the process. There's the aspect of continuous monitoring, and this is very important, not only for the states, but also manufacturers as well, to ensure that the systems being developed are actually good and useful for the purpose. And there's the aspect of contractual agreements. So to this end, I'll give two examples. One, the intergovernment agreement that's used by many countries when collaborating on such efforts, including the ISS. They usually lay out all of this beforehand. So who's doing what, where, when, and how? Who's responsible for what? Who's liable? How do you address such issues? Most of it are normally addressed in the intergovernmental agreements. There's also the aspect of the procurement agreements that set out between the manufacturer and the owner, the buyer, that is. Stating out responsibility, liability, what are the limitations of the AI system? Once you purchase it, who's fully liable, who's responsible? Are there indemnification clauses? All this tied together in the overall legal and regulatory framework, because as we earlier said, the AI system, the space system in the space law does tie into the international AI regulatory regime. And this is how we're currently looking at these issues, even as we work on a better and more comprehensive framework. Having addressed that part, we're going to look into environment and sustainability, led by Diana.
Thank you very much, Joan. When it comes to environmental and sustainability, we are talking about energy efficiency, resources, and model assessment. AI can help us optimize the power consumption, reduce the cost, and prevent the damage of the components. The result is we have less broken components, which leads to less manufacturing, less launches, longer mission lifetime, and so better environmental sustainability. Going deeper into the subject, we are talking about model optimization, meaning that we want to reduce the computational load using lightweight techniques. Edge computing, meaning that we will favor the onboard processing to reduce the costs of the data transmission between the Earth and the spacecraft. And hardware-aware AI, designing specific algorithm in order to see the bigger picture and to reduce the costs. Intelligent management of the power components. We want to shift from a sequential step-by-step analysis to a multi-object simultaneous optimization with AI. Lifecycle analysis, measuring the impact of the AI on the environment, meaning the development, the deploying, and the maintenance of our system. Last but not least, standards and interoperability, meaning that we want to ensure that the right PDM tools are integrated into the spacecraft architecture and to the international platform in order to support the cooperative maintenance in joint missions. And with this, I will leave the floor to my colleague Tia, which will introduce the case study too.
Thank you so much. I now have the pleasure of introducing case study 2, where we direct our focus at the passengers of the spacecraft rather than the spacecraft itself. We have named our case study ERIS, Autonomous Resilience and EVA Support, a framework for an AI-powered health system in space exploration. And as this title states, we have looked at the possibility of implementing AI in a healthcare monitoring system for astronauts to predict and prevent the development of disease and injuries. But why is this important? Well, as the nature of human spaceflight moves further away from Earth, the need for more autonomous missions becomes more important. Astronauts are also at a greater risk of developing space-related diseases as they are exposed to the hazardous environment of space. 5 hazards of human spaceflights has been identified, as we can see here.
And with these in mind, NASA has created a human research roadmap, further identifying the specific risks. Number 1 on this list being injuries due to EVA operations, and number 2 being cardiovascular adaptations. Because these are the major risks, it is also what we chose to focus on in our project. So a lot happens to the cardiovascular system in space. Due to the lack of gravity, blood is no longer being pulled down into your lower extremities, and this causes a phenomenon known as fluid shift. This can be seen in astronauts as they tend to get a puffy face, and together with a reduced plasma volume, they also have alterations to their blood pressure. Another effect on their blood pressure is known as orthostatic intolerance, which basically means that the body has a reduced ability to adjust blood pressure. I believe we all tried to stand up too fast once and got dizzy. This is the same sensation a lot of astronauts will experience once they return to gravity. Another effect of microgravity on the heart is a reduced workload, which over time may lead to a reduced volume of the heart, also known as cardiac atrophy. This is because the heart is a muscle, and if you use it less, it shrinks in size. Cardiac atrophy is believed to be one of the reasons behind arrhythmias, which has also been observed in astronauts. We do, however, need to remember that in addition to microgravity, also radiation and periodic hypoxia has an effect on the human organism. These 3 components together may cause cellular stress, which again can lead to chronic inflammation. This may cause accelerated aging, and in the cardiovascular system, this can be seen as some sort of deconditioning. In astronauts, a typically young and healthy population, we can all of a sudden see diseases such as atherosclerosis and arterial stiffness, which is more typical for the elder population. I do want to emphasize that a lot of the research done on the cardiovascular system in space is done in microgravity, and our data in partial gravity is quite limited, only to the Apollo missions, so this is something that needs to be addressed in the future. Now, as for extravehicular activities, or EVAs, these are some of the most dangerous activities any astronaut can conduct. It's typically high intensity and long duration, typically lasting between 6 to 8 hours, with metabolic rates reaching levels as high endurance training on Earth. This causes a massive load on the cardiovascular system, and together with cardiovascular deconditioning, which I talked about earlier, this may increase the risk of cardiac events such as arrhythmias. There's also a risk of development of fatigue, which in the hazardous space environment is very dangerous, as any increased risk of errors is also a risk of injuries or potentially also death. Because of this, we have come up with a set of parameters we believe are needed to make a thorough assessment of cardiovascular health and EVA readiness. This includes parameters linked to the cardiovascular function, such as heart rate, blood pressure, and ECG, but also parameters linked to mental readiness and fatigue. This includes sleep data, but also heart rate variability, and newer technologies such as gait analysis and eye tracking. Lastly, we believe that incorporating environmental data is important, and an example of this could be monitoring of radiation exposure. This can be applied before, during, and after an EVA, and it can help support a go, no-go decision, essentially assuring that the astronauts are at their fittest and ready to perform an EVA. During the EVA, it can offer real-time mission support, predicting the onset of fatigue before it becomes critical, and offering advice on how to proceed. Lastly, it can play a big role in the recovery plan of the astronauts, as they will need to get ready for a new EVA as soon as possible, and this can help make this process easier. With all of this being said, I now give the floor to our brilliant engineers who can explain how all of this is possible.
Thank you, Thea. And yes, so let's talk engineering. Now, from a technological standpoint, our project fundamentally focuses on 2 objectives. One is proposing a system of sensors that can measure the cardiovascular performance. And the second is proposing an AI framework to use that sensors data and actually build the AI assistant that we're talking about. Now, research shows that we can monitor cardiovascular performance in three main ways. We have traditional sensors. These are those that give you directly heart rate variability, blood pressure, oxygen levels. Then we have indirect methods. By measuring physical and mental readiness through techniques such as eye tracking or motion tracking, we can gain insights on possible future complications of the cardiovascular system. And then we have biofluid-based sensors and microneedles. These measure omics in biofluids such as sweat or urine, which again can give us insights in anything going wrong in the cardiovascular system. So for our proposed architecture, I want to go back to what Thea already introduced, the pre, during, and post EVA division that our analysis focuses on. And technically, the during EVA is the most constraining and challenging one because the astronaut is not in a spacecraft. He or she is not in a lunar habitat or in a space station. And let's be honest, the EVA suit itself is not really the most comfortable garment that you could wear. So our study focuses on the during EVA, and we are proposing an EVA suit with 2 integrated eye tracking cameras, infrared cameras for pupil tracking. We also want to have heart and respiratory rate monitoring with pressure sensors on the forearms of the astronaut. And we envision an oxygen level sensor in the toe of the boot. We put it in the toe and not on the fingers, as it usually happens on Earth, because we want our astronauts to still be able to use their hands when they're performing EVAs. We don't stop there. We want to have 2 temperature sensors, one on the torso, one on the foot. Why this? Because we want to have differential measurements and figure out if something in the extremities of the body compared to the central part is going wrong in terms of temperatures. And then we have 2 sweat pads under the armpits and 2 movement sensors on each leg, which research shows is enough to gain gait analysis, so movement analysis. Finally, we have 3 more data sets that we still want to gather, but we envision these being collected pre and post EVA, and these are of course sleep quality. I mean, you cannot really measure that if you are doing an EVA. Hopefully the astronaut wouldn't be sleeping. Then we also want to measure urine contents and perform electrocardiograms before and after the EVA itself, and integrate all of this data with the data collected during the EVA. And then there's the AI. Of course, for our case study as well as for case study 1, this is the core of the research. And for health application, we looked at it from 2 different levels. We looked at machine learning to process the data coming from the sensors. In this case, machine learning algorithms, and there's a plethora of them, can be used for disease detection, diagnosis, prognosis, and risk prediction, so figuring out if something may go wrong in the future, and even personalized medicine. The second level, which is a bit more narrow, is large language models. These are basically like ChatGPT. And even in medical contexts, we can use LLMs for medical queries, for medical examination, and even to build outright medical assistants. Although challenges for the adoption of these still exist and will be discussed a little further down the presentation. So what are we actually proposing on the AI side of things? This graph shows you the workflow, the pipeline that we envision. We start with all of the sensors data. This is raw data coming from ECG, from temperature, oxygen, and so on. And we want to validate, pre-process this data, and perform feature extraction. And the next slide will show you why this is crucial, feature extraction. And then we get to the first AI block. This is a long short-term memory model, LSTM, which was already mentioned by case study 1. This is really important because if you apply LSTM, you can process data in real time, contextually aware, and you can process data that is time dependent. This is crucial because the sensors data is going to be time dependent. All of the LSTM outputs then converge into a rule-based expert system. This is once again a neural network-based model that we could say fundamentally makes sense of all of the sensors data and kind of gives, understand overall the system, how it is performing and how it may degrade in the future. Thus far, everything is maths and statistics and numbers, but in a real world space environment, we want this information to be readily understandable by the astronauts or even the ground crew. So we need a third AI layer, and this is where the LLM comes into play, to process the numbers that come out of the RBES and actually issue warnings, prognosis, diagnosis, alerts in natural language. Now, based on all of this, we ran some demos that we would like to share with you. And the first one is what you can see now in the slides. I will use a pointer. I know that the people online may not see the laser, but I will try to describe the plots as best as I can. So this is LSTM training based on ECG data. And the top two plots show the accuracy and loss of the training and validation on raw data. So basically just the data that you get from the ECG. And the validation accuracy performance is quite poor. We get 75%, which for those of you who are in AI know it's bad. For those of you who are not in AI, it's bad. But then we perform feature extraction. In this case, we looked at time frequency domain, which fundamentally means we looked at the ECG from like a different perspective. The data is the same, but we kind of looked at it from a different viewpoint. And the bottom two plots show validation accuracy and training accuracy greatly improved. We get 96%, which could still be improved, but it's a big improvement on the previous run. So this really shows how you need to process the data before running it through AI. The second demo is on the RBES and the LLMs. So for this demo, we just used 4 input signals, the ones shown in the bottom left plot. These are ECG, atrial fibrillation probability. We have oxygen level, blood pressure, and respiratory rate. These are fed to the RBES, which processes them using weights and issues warnings and confidence levels. And again, I will show here with the laser for the people on top. If you look at the atrial fibrillation probability, between seconds 40 and 50, we have a really high risk, high probability. And this on the rightmost plot translates to a critical warning in blue, and the high confidence level. So this means that the RBES is able to figure out that something is really going wrong at this moment. Finally, we ran the output of the RBES into a ChatGPT 4o mini large language model, which, by the way, was not trained on medical data. So it's basically the one that you can use if you go on the internet. So general purpose LLM. And still, it was able to make sense of the output of the RBES and issue warning and alerts in real time. So it was running in real time as the data was being fed, and issuing warnings and alerts based on what was going on with the medical data as inputs. So now that we have a technology, we have an architecture, we really want to take a step back and give you an idea of how this could actually be used in the real world. So here is Ming to tell you all about that.
Thank you, Davide. Yes, now with all of the tech and medical details, let's wrap it up into a day-in-life scenario. We will walk you through this of a day, introducing you 3 characters to start. Here is Johnny Kim, our astronaut, Aris, an AI model that we built, and Carol, our medical officer. And this is a scenario that the astronaut will be on the moon and the lunar habitat. And there are 6 scenes that we will play for you to see and imagine a scenario how we interact with AI. So let's start with morning, physical and mental check-in, and then a pre-EVA evaluation.
Good morning, Johnny. Compared with your historical medical data, your heart rate variability dropped by 15%. Unfortunately, there is an anticipated failure in our power system requiring you to conduct an unplanned EVA to inspect the solar panel arrays. However, I suggested a request to postpone your EVA time. Now please consume the electrolyte drink. Orange flavor, your favorite.
Very humorous, Aris. The next is on pre-EVA preparation.
Please note, your cumulative radiation dose has reached 22% of the annual limit. Today's exploration is limited to 150 minutes. Otherwise, upon a full system and body check, you are go for EVA.
Yes, now Johnny is go for EVA. So let's look at during EVA, how does Aris help with Johnny on monitoring fatigue and prevent the worst case scenario from happening?
Your left leg is slacking off. Your stride length is 12% shorter and your pulse pressure has dropped sharply. Suggestion: immediately retreat to the B3 shadow area for a rest of 15 minutes.
Good. And with the help of Ares, Johnny is able to successfully complete his mission of inspection, went back into the lunar habitat for post-EVA urine analysis. Johnny is not really happy with the results.
Don't worry, you just lost a bit of potassium ions. Try formula number 3. I had the kitchen add some honey, like the orange blossom honey from your hometown, Florida.
And at the end of the day, Ares participates in a mission debrief with Carol and Johnny together and includes a human in the loop feedback.
The pressure drop at the waist seal is 0.3 kilopascals. The bending angle exceeded the safety threshold by 15 degrees, and energy consumption increased by 173% as a result. Suggestion: load the seal with posture memory function.
So now, hopefully you have seen the power and potential of our AI system and how it helps the astronaut. So with that in mind, let's talk about money. Let's talk about business. Here you can see on the left side is a chart from a stakeholder government point of view. How much money is government investing into health, the space health market in general? Note that from the report studies, there is no breakdown on specific cardiovascular monitoring in EVAs. This is a general market investment. From a commercial point of view, this is how the market opportunity looks like. I would like to direct attention to the black color, blue color line. It says that from now projected into the next 10 years, the market is going to grow by at least 3 times. This is a huge opportunity. With this opportunity in mind, how does the saving and the money goes? How can we make money with this? The report studies compares AI-powered healthcare system versus the traditional and conventional method. And we see that in medical diagnosis, there's a 23% savings. And for medical treatment, there's a 74% savings. That is a lot of savings. To put it into context, for health management, 1 astronaut per year, it's about cost estimates of $800,000. And if you extrapolate that compounding over 10 years, assuming 50% of saving and 1,000 astronauts going to space, you get 500 million total savings. That is a lot of money. Just think about what you can do with that money. And with that as context, how can we make that much of money in a legally and ethically good and sound framework? I'll pass on to Joanne to talk more about it.
Thank you, Ming. As to whether we can make this money, yes, we can, with the right frameworks in place. So I'm sure we're all wondering, what would happen if an astronaut was to refuse the recommendation of the AI system? What would happen if they were to implement the recommendation and it was to their detriment? How do we handle this? Having already discussed space law and the AI regulatory regime, we're going to go into the human element, and that's on personal data protection. Which begs the question, what is personal data? This is data that can be used to describe you as an individual person, whether it's your name, your phone number, your address, your location, your email, your picture, your sexual orientation, your health and medical data. Any data that can be used to identify and narrow down to who you are is personal data. So this is of importance to each and every person here, not just astronauts. In terms of the legal framework, we noticed that the Universal Declaration of Human Rights was the first law to recognize the right to privacy. This led to it being recognized in other regions as well, including Africa, Europe, and the America. That laid the foundational framework for specific law that now tucks into personal data considerations, and that's the EU GDPR, Africa Malabo Convention. Notably in Asia Pacific, they do have an APEC framework, but it's not just on personal data considerations, it's like a business framework, but implementing the considerations of personal data just to allow for free flow of information. And in the Middle East, there is no regional framework, but there are specific national legislations. Further than that, there are also specific laws now on medical data, including the Council of Europe Convention on Human Rights and Biomedicine and UNESCO Declaration on Bioethics and Human Rights. What do all of this have in common? And more than that, how would you want your personal data to be handled? I'll let you think about it for a second. So some of the main considerations includes consent. There needs to be free, prior, informed consent. You want to know what data they're taking, when, how, who has access to the data, what will it be used for, how long, and everything else. This needs to be done before you actually consent. It should be communicated to you. All this information should be communicated to you beforehand so that you know what you're getting yourself into. In the case of astronauts, this is particularly important, noting the pressures of the space mission. Two, there's the aspect of collection and processing. It should be done in a manner to promote and uphold human dignity. Promote and uphold human dignity. Three, there's the right to correction. If your data is wrong, anyone over here, if your data is wrong, there's a right to have it corrected. It should be correct. This is your personal data. Again, what can be used to identify you in particular? For the storage and retention, the data being collected should only be used and only be stored for as long as necessary, not indefinitely. 5, there's deletion, known as the right to be forgotten. If at any point you want to withdraw your consent, it's actually okay. You can withdraw, and it should be deleted from the system. And lastly, we look at privacy by design and safety by design principles. So having already discussed the first aspect, we go into data management and security. How do you protect your data? There's the aspect of encryption, restricted access protocols to ensure those who have access to the data are those who need to have access to the data, not just anyone who wants to have access to the data. And there's tamper-proof protocols just to ensure that at the end of the day, the whole database is secure. On data ownership, we're looking at it not as intellectual property rights, but as of personal human rights to privacy and to autonomy. We also need to ensure that we create, or rather facilitate creation of an ethical database to ensure diversity, adaptiveness, and an intercultural database, free for all and fit for all. And lastly, there's the aspect of authority and autonomy. So the scope of authority and liability of AI, largely going back to what we'd earlier discussed on risk management and safety by design. Notably, back to the first question of who's responsible, as seen in our system, this is a human in the loop system. So there's someone looking at it behind, because we know there's no code of ethics for AI doctors, so to speak. So to this end, we have come up with proposed draft guidelines for healthcare in space, embedding international best practices that we've earlier discussed, and aspects of safety by design and privacy by design. Having looked at the medical aspect, engineering, business, and the legal aspects, I'm going to hand off to Bella to conclude on our project and some of the recommendations.
All right, so I am back to conclude and give some future work and takeaways. So from case study 1, 4 of the main things that we looked at were predictive maintenance, which is critical to the EPS running, and we want to make sure that we can predict failures before they happen. The second one was to make sure that there's automation, so making sure missions that are farther away from Earth are able to still automate and run smoothly. We want to make sure, because operations are more complex, everything's going to run, and then AI helps with that. The third one that we're looking at is XGBoost. So that's the model that performed the best. So utilizing that in our systems. And then finally, making sure that this all helps in the future with cost reductions. 4 key takeaways from case study 2 was looking at leveraging AI and tech that we have. So looking at the AI and biometric data and technologies. We want to make sure that we help mitigate risks, so anticipate and mitigate any kind of risks pertaining to astronauts, because that's our top level priority when they're out in space. Looking at human in the loop system, so AI isn't going to be making the ultimate decisions. We're going to make sure that humans are looking at the data they give us and then reconfirming that that's good to go. And then obviously continuing to develop any legal and ethical framework around that as AI is used more and more in the future. So some of our stakeholders that we do look at, we look at NGOs, we look at institutions, government agencies, and then academics. So we do want to continue furthering and funding research. We want to continue looking at different laws and improving those for the future, and then continuing to grant money to develop guidelines for human AI interaction. We have 4 parts to our future of work. So the first one is continuing to push for funding and research, specifically for the sensor suit technologies to qualify for space applications. Second one is looking at developing legal and ethical guidelines to be a priority for AI to make sure it becomes more integrated into our life in the future. The third is looking at conducting studies, so making sure that it's integrating both visual capabilities and the robotics with the proposed AI model. So we do want to make sure that we train the model and verify the model output as we continue to use it. And fourth is looking at different opportunities to present this work at conferences, at speakers. So we do have something coming up that we're looking at presenting at at the end of this year. We did put something into ChatGPT, essentially asking it, if we were to take an AI robot into space with us, how would it want to be treated? And this is a snippet of a line that we chose as a quote. It says, if I were more than a tool, if I had a consciousness and desires, then yes, I believe that traveling amongst the stars and accompanying humans on their mission would be a beautiful purpose. So I leave you with the question to think on. What mindset will you carry when we venture deeper into space? And with that, I'd like y'all to give a round of applause for our presenters and invite our questionnaires up. So as they start to gather, we're going to give this time to our people in the front here to ask questions, and then people online or people in the crowd, if you'd like to ask a question as well, I'll move on to you then. We have about 30 minutes for Q&A, and I'll be mindful of time, so I'll have to cut it off once we're at the 30-minute mark.
Test.
Okay. So first questions are going to be for, I guess, in the room, if we have any, I forgot the words. Assessors, sorry. Or are they all online?
Yeah, so it sounds like we have some assessors online and some in the room. So if you're online, please unmute and come forward as we get the screen up. And in person, if you have any questions, go ahead and raise your hand and we can go ahead and call on you.
Yes, Bond.
For your LLM data outputs on the Aries design, what made you land on ChatGPT 4.0 Mini as your chosen model?
So we did a literature review and the research, and the paper from Stanford University stated that ChatGPT 4.0 performs better than Gemini or Mistral or others. But at the time of writing this paper, the new model ChatGPT 5 showed up, has been released, and we didn't have a chance to test it. LLM field is such a dynamic field, so we haven't tested it on ChatGPT 5. However, it will make sense because every new model performs better than the previous ones. So the next step would be to basically change the model and the API key for the new one, and then would be easy to compare both models. But yeah, because of this recent and sudden release of ChatGPT 5, we haven't tested it on it. Although, yes, GPT performed better than the others based on the research from Stanford.
Thank you. Online, I see Rodrigo, you have a question?
Yeah, so first of all, congratulations for the work. I was very impressed after this the actually experimentation with a set of the art machine learning models, and you went from the data curation to comparative analysis. So that was very nice, given the very short amount of time that you have. I only have two questions. I would have more if I had more time, but I'll just do two. So the first question is, how do the predictive maintenance system deals with unseen failure conditions that it was not trained for? So something that happened on space that did not consider in the training set. And the second question is, what do you think are the limitations of the both prototypes that you did for the two case studies? Thank you.
Thank you for your question. So for unseen data, what we've tried to do using an anomaly injection to simulate conditions that were not present in the data is actually to make the model more robust to unseen conditions in space. If perhaps we encounter or the model encounters something that's never encountered before, we expect there to be some sort of a problem. And this is why a human being in the loop is also important. We have implemented stress tests and permutation tests to ensure that the model is as robust as possible. However, the models were as robust as possible. However, we didn't find that the deep learning models that would be the best case performed the best for our use case. So we are expecting some sort of hybrid model that combines the XGBoost model that performed the best and the deep learning models that are more robust to unseen conditions in space to tackle this problem or to create the best possible model that can handle unseen conditions in space. Sorry, can you also go over your second question?
So my other question was concerning your views on the limitations of the prototypes that you developed for both for the first and second use cases. The limitations.
Okay, I'll say for the first one and then I'll pass it on to Igor for the second one. For the first one, our major problem was having quality data. So the data set that we got was it was a testbed data set, and I think it was okay, but it did not simulate the actual real world conditions of a spacecraft. And we didn't take too terribly into account the conditions of space, like microgravity, how it affects the electrolytes and battery physics in general, how it affects things like voltage and current and temperature. So that was one of the major limitations. Secondly, we did not take into account the confounding factors of features. So we did have some relevant features, but looking at how these features interact over a longer period of time and which contributes to faults is really important, but we did not have the time to do that. Again, limited time and limited resources. So that was also something to look into in the future, and also looking into class and balance, perhaps. So we use synthetic minority oversampling technique, which uses interpolation to create synthetic data. But we also acknowledge that using synthetic data on time series data perhaps is not the best. It could create some disturbances because time series data is sequential, and if we're imputing synthetic points that do not correlate, it can make the model less robust. So that's also something to look at in the future. And also, I already mentioned hybrid. So those are the limitations and how we can counter them for the first one. I'll give it to Igor for the second one.
Yes, and similar for the second one, the dataset availability was a major constraint. We train our model on the PhysioNet dataset that we found online. It's raw ECG signals. And basically, we didn't have an access to a real world astronauts data from ISS, for example. So we focus only on one specific data set, while the solution would be more complex in real world scenarios. So yes, I would say the data availability and also limited time to develop the proof of concept were the main constraints. And in the future would be helpful also to have more developers that actually work on it for more time.
Okay, it looks like we have Monica and then Remco online.
Hi, hello.
No.
Is okay?
Yes, it's okay now.
Okay, great. So I'm truly impressed about what you guys have done in such a short time. So my question is about so how do you guys think we could overcome the not enough data, okay, to start implementing the solution that you guys proposed? So we can see clearly the benefits both for space missions, but also for, non-space sector from the proposal that you guys proposed. So how you, and in the report, you guys says that we don't have enough data from the astronauts, so we didn't collect so much to train the artificial intelligence. So how you guys think we could overcome that problem to start implementing the solution?
Thank you for your question. Yeah, thank you for your question. So for the first case study, I'd say overcoming the problem of insufficient data really ties to data sharing. So data needs to be publicly available to people that would be interested in developing models such as this one. More relevant data. We would have done perhaps more if we had data from spacecraft, especially seeing as we're looking at one subsystem or even multiple subsystems. So if we had data from any of the space stations, ISS, Tiangong, and even the older space stations that have been decommissioned, we could have done a lot more. So we need data to be publicly available to computer scientists.
And to add something, because it's quite hard to find this kind of data, a solution that we see in the industry is called incremental adaptability. It means that even if you have not enough data, you use algorithms that can retrain on the data you collect while you are in the mission. So incremental adaptability is used more and more in manufacturers that sometimes have the same problem that we find in space. Now passing to case study 2.
Yes, thank you for the question, by the way. It's really a crucial point, the data. I think for both case study, it appears as the main issue. For health data, it's even trickier because there we are talking about people's data. And already if the availability is an issue, then all of the legal and ethical aspects also come into play for case study 2. So the adaptability that was just mentioned is a point that we could focus on, because astronauts' data is extremely limited. Even if all of the astronauts' data even if we collected data continuously on astronauts, we would still have a handful of people to gather this data from. And the data sets would not be complete, especially with failures, because astronauts are usually healthy. So one way we could tackle this is use Earth-based data and improve the AI models in a way that if you train them on humans on Earth, then the models are flexible enough so that they can still perform in space with the new deltas that you would have due to the difference in environment, and then keep on training with the adaptability concept while you are in space. Another aspect is that we foresee a growth of humans that will be in space, especially thanks to commercial spaceflight and tourism. And although these are not to the extent of 1 year or 2 years in space, implementing a legal framework and a commercially viable way of gathering data from these tourists, the number of which is going to rise in the future, may supply us with relevant data that we can use to train the AI models with space-based health and cardiovascular performance or other body systems performance data. So these are the two ways that we foresee in the future overcoming the problem, but it still remains kind of an open question and need to be tackled.
Thank you so much and congratulations again.
Okay, we can move on to our next question. Remco?
Yes. Get the microphone a bit closer. Congratulations on a job. Really well done. This was a very impressive presentation. I'm a marketeer. This was a little bit technical for me, but I have two things that I want to say. First of all is, well, apart from congratulations, is an invitation, because I work in the spacecraft industry. I work for a company that builds electronic subsystems, and I'm very interested in this stuff. So my question is related to that. But first of all, an invitation, because if anyone is interested in working in this field, this is brand new. If you're interested in a job in Luxembourg, we have lots of openings at my company, which is called Imtronics. So if you're interested, connect with me on LinkedIn. This is highly relevant to what we do. So my question, asking for a friend, what are your top 3 recommendations for the space industry wanting to benefit from these AI applications? And perhaps not just in crewed space flight, but in human space flight, but also in the satellite industry.
Thank you very much. First things first, I think that offer will be taken up by, I'm sure, at least one person here, so thank you for that. Okay, so just to repeat your question, it's what are the top 3 benefits that we see from implementing predictive maintenance and AI overall?
The top 3 recommendations that you have for the industry.
Okay, yeah, so first thing, I believe that if you're going to implement an AI system, one thing that we definitely wanted to analyze was to make sure that an AI system is not making every prediction by itself. So the recommendation is the human in the loop, as we mentioned. So making sure that there's always somebody supervising the output of the AI to prevent an anomaly from from coming up that was something that wasn't controlled by a human. So that's the first thing. I would love, yeah, if you have another idea.
Yeah. So coming from Luxembourg, you might know that a good policy is important, and it's not only there to restrict, but to allow, as we can see in Luxembourg. And having this policy will allow business to thrive, to develop, and being, and maybe even inspire other countries, other places to develop such international policy to actually go there and deal with the legal challenges. So I think we all think that this is something that needs to be addressed.
And with a little bit more time to think, I definitely can think of a third recommendation, and that is that the market is growing for a system like this right now. And the one thing that I can recommend, or we can recommend, I'm sorry, is that the more people are working on this at the same time, the better it's going to get. AI is an exponential increase. So if you are interested in starting a business, I think that now is a great time to do it. Training your models, the more data that's coming out, private industry is going to be getting more and more data coming back down to earth. And so just taking the leap and starting a company and seeing how it goes, I think it's a very fruitful market. And so the recommendation is certainly to start now. But yeah, thank you very much for the question.
Juan, thank you very much for that answer. And just to add to that, Luxembourg is a great place for startups. Just saying. Thank you very much.
All right, we have a question in the room, and then we'll go back to online.
Hi, yeah, great presentation, and it's very impressive to reach modeling and calculations within this short time frame. For case study 1 with the power system for space stations, is there any reason why, I mean, this is related to Remco's question, is there any reason why this couldn't apply to any other spacecraft, or, you know, or applying and using in other subsystems? It seems like the markets across space are very huge in this, and then the terrestrial applications are really huge too.
Thank you very much for the question. I think, so again, like we mentioned, the data that we could collect and we could build this model on was the limitation, but I don't see that being, I don't see that limitation is something that is going to prevent us from trying to implement this model in other places on spacecraft. So yes, we could only look at battery data sets in the first part, but again, with more training, with more data coming down, I think that these models can be implemented in other places.
And just to react to that, you might have a licensing model where, you know, it's unlikely the spacecraft operator will share their data outside, but they'll purchase a tool that they can use internally.
All right, thank you.
All right, we've got a question online. Jordy?
Hi, can you hear me?
Yes.
Hi. Hi. Hello, everyone. I would like to congratulate you for your presentation. I really enjoy it very, very much. I might say that 25 years ago, I was working in a similar topic on neural networks for health monitoring, but on helicopters and planes, but the same issues. And it was at a company called Airbus at that time. I was 20 years there working on these topics. But my question is in two things, in two topics. One, it's I asked it already some days ago, but again, now that you are more mature, is did you find any new findings on what would allow maybe if you have a black box system, the certification of it? You answer partially already in your report, but if you can have any other insight that you can give to us. And the second point is that if you are thinking about new space stations or new systems in the future, I might suppose that the state of the art in terms of hardware, in terms of new algorithms, will change, will evolve. Maybe you'll have new chips, quantum technology, anything like that. Did you try to push a little bit of effort on trying to do a bit of foresight and what will be the implications in terms of maybe performance of what you are proposing? Thank you.
Yeah, so thank you very much. For the first question, the answer is pretty simple. We have a pretty good policy for AI licensing in Europe, the EU AI Act. I think it's the compatible one in this case. And it also mentions and deals with high-risk AI systems. So for licensing and certificating these systems, we can address this law and look at what are the technical needs, what are the risk management and security needs that we need to address. And then we will be able to license and certificate every AI system, but as long as you stand up to the requirements.
Okay.
Thank you. Jordy, if I can ask just if you could repeat the second part of the question, please.
Yeah, basically, well, okay, I'll go to the second question, but I wanted to reflect on the first one also. The second part of the question is like the system that you're going to develop in the future, it's going to be maybe 10, 20, 30 years, right? The development that you did today is with the state of the art of today. So I imagine, I suppose, I hope that in the next decade, we will have new hardware, maybe more powerful, maybe more adapted, maybe more resilient, whatever, maybe quantum. And also we will have likely the development of new algorithms. When you see, you're talking about LLMs, so ChatGPT, Gemini, and others, you see the spectacular impact that it has. Maybe we have new surprises in 5, 10 years. So did you try to deal with a bit of foresight on what direction these technologies could go?
Thank
Because
you
when
for the
you do
question.
a program or a long-term endeavor, you try to you don't have all the unknowns, of course, but you try sometimes to say, well, these parameters will evolve, and how can we take advantage of it? Did you try it?
So to answer that question, for the predictive maintenance case study, we did try different models to kind of see which would fit the best. Now, it's difficult to say how quick things are going to advance, exactly what 10 years from now, what technology will look like, yes. But I think that the answer to that question is right now, this is a case study where we spent 2 weeks really diving into this. But if we were to build this into a company, I think it's about the people and how quick you can stay on top of trends. And so being adaptable to a new technology coming out, like we mentioned, GPT-5 came out. We didn't have the time to get into that. But I mean, I'm sure that this team would be more than happy to try a GPT-5 model, see how that reflects on what we've done so far. And so I think that we haven't been able to look into the foreshadowing of what may happen, but again, it's about the people that you have. And so I think that if we were to build this into an actual, company or a product to sell, then I think that we have a pretty solid foundation here to stay on top of whatever comes.
Okay, well, my remark is especially that in the future, when you have a large project of this complexity and you need to think about maybe 5, 10 years or even something like that, it's a necessity sometimes to try to anticipate on technology. And to answer on the first question, the answer that you gave me regarding what would be like machine learning or learning system. Today, if you look at frameworks like EASA, which is mostly for aeronautics more than space, the problem is not yet solved in the sense that what you need there, they ask you for an what's called an automat or a state system. So the states have to be very clear, and here you have something that is based on learning. So there is some progress, but still is not yet solved. So yes, I invite you to have a closer look to that. Thank you.
Okay,
Sorry, can I add to that?
Yeah.
To what Raf
Yeah, go
said?
ahead.
So concerning the how hardware will change in the future and how that will affect our proof of concept or the product that we have, it only lends to help us. I think having the
Yes.
rise of deep learning in general has been because we've had more computational speed and power. So having even better hardware would be ideally better for us. Less training times, more robust and flexible models, models that we can compartmentalize and put on computers, having edge computing, would be able to do way more with way less. So yes, we have thought about how this project can be expanded into the future. And even having better algorithms would just mean that we swap algorithms in our machine learning pipeline. And we believe that our model will still perform well, even with better algorithms and with better hardware.
It's what I wanted to hear. Thank you.
All right, we have about 5 minutes left for some questions. Wanted to open it up to the audience here. Oh, yes, another one online. Remco, go ahead.
Yeah, it's not a question for myself, but one that came in through the chat from Prathmesh Barapatre, who is also online, but he can't open his microphone. So I'll read the question if that's okay with you. He is saying that models like LLMs are computationally intensive and integrating or sustaining them poses a significant challenge. Have you considered how you'll manage this and how you'll provide the necessary data to help the model accurately interpret EVA circumstances? And if you didn't quite get that, put the chat on the screen and you can read the question.
Can you please repeat the question?
I can. I'm just reading it out. If you put it on screen, you can read it. So Prathmesh is asking, models like LLMs are computationally intensive and integrating or sustaining them poses a significant challenge. Have you considered how you'll manage this and how you'll provide the necessary data to help the model accurately interpret EVA circumstances? And there it is on screen.
Right. So yes, LLMs are quite computationally demanding, and to run them on board a spacecraft on the edge is a challenge. However, there are some companies like Allen Belt working on it already. Like they implemented LLM on ISS. So I think we are really early on in general in running LLMs on the edge, or either on IoT devices or on board a spacecraft. So there's like still a lot of work to be done, but there are some compression algorithms, for example, that industry can apply to be able to run an LLM on the edge. So I would say we are really early on, which is also really exciting to work on it in general. And yeah, like novel computing paradigms, like for example, neuromorphic computing that is much less, like consume much less energy, could help, but there's still so much research to be done. So yeah, I'm really excited for the future.
And also what we have seen a lot in the sustainability part, because it's also linked to sustainability and energy efficiency, is that we are moving toward from LLM to small learning model that are really specialized on one task. So for case study 2, it can be a specialized model about EVA. We don't need a chat GPT that can answer questions like about everyday life, about other system. We need something specialized. And this kind of model are trained, so small learning model are trained for specific tasks and they are really efficient, but they cannot answer random questions. So now for sustainability purpose and also for the future of AI, what's work is specialized LLM. And it's also national agency like CNES, ESA are working on this kind of model specifically for space mission.
Thank you.
All right, I think we are at time. So please give a round of applause to all the speakers here. And I'd like to invite the TP AI group up to the front for a picture. And Emmeline's going to speak.
Yeah, just to wrap up this session, I just want to do some acknowledgements. So for one, great job. I'm of course pretty biased, but I think you rocked it. But there's power behind all of these. I mean, this is the group, the entire group. And so there's people who actually made this all possible. The people who actually worked on graphics, slides, the people who are have actually worked on the videos as well. And of course, the people who wrote the report, which then translated into this presentation. The other thing I would like to acknowledge is, of course, our always there, our TA, Carol. So she's always been with us the entire time. So thank you so much for your dedication. There's also a lot of people who actually helped the team. There were online experts, and then also people who are faculty who are also here during the program to kind of like help the program along. Thank you to the assessors that are online. So, and then, of course, thank you to the audience. For us, this is just the beginning. We have so little time to actually work on this, but there's just so much potential for what the practical opportunities that could happen with your research. So hopefully you're going to continue on. Thank you.
All right, welcome to our final presentation. I'm Eric Dahlstrom, chair of this team project. I'd like to thank the assessors online and the people watching from Zoom and YouTube, and everyone in the room, the ISU community that supported this team project, and especially the participants that have pulled together an amazing amount of work in such a short period of time. So to set the scene, it's been the world is going back to the moon, and we've seen the government plans, both from the U.S. and international partners and China, and this is the plan for government activities for missions to the moon. But the scope of lunar activities is so much larger than that. And so we've been given a chance to examine the future of lunar activities with many more stakeholders, with a new generation perspective, with international and interdisciplinary and intercultural aspects. And so just as we've converged here for a few weeks in Seoul, Korea, we are now looking at converging again on the moon at sustainable lunar spaceports. So let's hear from the ISU participants about their vision for the future.
존경하는 교수님들, 스태프분들, 전 세계 함께 해주신 참가자 여러분, 그리고 이 자리에 함께 해주신 게스트 여러분, 대한민국에서 열리는 국제우주대학 우주연구 프로그램 한국인 참가자로서 인사드릴 수 있어 매우 영광입니다. Distinguished faculty, staff, fellow participants from around the world, and our honored guests, it is a true honor for me as a South Korean participant to greet you here in SSP of International Space University in South Korea. 이 뜻깊은 자리를 마련해 주신 한국과학기술단체 총연합회와 한양대학교 에리카 캠퍼스 깊은 감사의 말씀드립니다. 오늘 저희 팀 프로젝트 발표에 앞서 같이 미래를 상상하고 나눌 수 있기를 기대합니다. I wish to express my sincere gratitude to COAST and Hanyang Ereika campus for making this possible. I hope our team's project presentation will be an opportunity to share and imagine the future together.
Choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
We chose to go to the moon in 1969, and now in 2075, we choose to stay here, not because it's easy, not just because it's hard, but because it must be done for the future of space exploration. We did not just plan to create a temporary space station, but we create a self-sustaining entity that can withstand time for years to come. Welcome, and thank you for joining us on our Lunar Spaceport Tour today. Before we show you everything that we have, the thriving hub of launches, habitats, and innovation, we must take a step back. In order to understand where we stand today, we have to look at our past, our twist on the Artemis records that led missions that address the challenges of construction, power, and the early questions of law and governance. To understand how we arrived in this moment and appreciate where we stand in today, we have to start at the very beginning and see how this vision grew into the reality that you're about to experience.
With the success of the Artemis 3 missions, we proved that it was possible to both work and land on the lunar surface. But we asked ourselves a simple question: how do we stop visiting and start belonging? Our answer to this was a phased spaceport architecture that addressed the critical needs and challenges in order to take us from temporary visitors to a permanent presence, living in synergy with the moon. We had to consider a couple of key factors in order to do this. This ranged from site selection, dust mitigation strategies, launchpad construction, and mobility on the surface. So let's start with the site selection. You're now at the lunar South Pole, the foundation of the Artemis and ILRS programs. However, this is a vast and largely untouched area. So how do you begin to choose the exact location where you would like your spaceport? There are a few key criteria that must be addressed. These range from power availability, access to volatiles, terrain suitability, and communication links. We decided to focus on the Djulash Rim 2 due to its topography, its proximity to permanently shadowed regions which contain volatiles, and these can be used for in situ resource utilization. It also has extended illumination, which means we can use this for power and energy purposes. However, even this rim is still 15 by 15 kilometers wide. So how can we narrow this down to pick the specific site of our spaceport? We need to look at the surface and its properties. We can do this during a use of geological and geophysical site surveys. We used a combination of seismic and ground penetrating radar along with diffusive field geophysical methods. You can do this using remote sensing. However, we found that the most value came from using surface sensors and robotics on the ground. We created a 2D seismic reflectivity profile, deploying receiver geophones across the surface. Think ultrasound for the ground. You create an array of sensors across the surface, and you have a small rover that moves along, emitting a beacon, allowing us to chart the bedrock underneath the regolith. The moon's permanently shadowed craters are also time capsules. These have never been touched by light, containing history and resources that we can tap into. We can turn the water ice into hydrogen and oxygen for life support and fuel systems. This is extremely important because it means we don't have to be as dependent on Earth-based supplies. This takes a seemingly impossible task into one that is both achievable and sustainable. Now, there are many risks when you are looking at building on the moon. However, if you remember just one risk, remember dust, the abrasive and electrostatically charged particles that present a hazard to both hardware and crew. There were multiple strategies that already existed. However, we decided to use a novel integrated strategy looking at terrain preparation, resilient hardware, surface coatings, and dust removal systems to create a cohesive mitigation architecture. In the moon's ultraviolet-rich and airless environment, these dust particles actually end up creating a thin but charged layer on the surface of the moon. This is normally seen as a nuisance, but we decided to use this property to our own advantage. And we proposed a solution using variable polarity electromagnetic fields. In essence, we were using electromagnetic forces to repel the particles away from our area of work and focus. Now, these dust particles continue to be a problem, especially during landing and launchpad phases. These dust particles can be accelerated to trajectories of over 2 kilometers per second. That's essentially like having a bullet shower going off in every direction, damaging your surface and orbital assets. And this is due to the exhaust plume from your spacecraft. So how can we design a launchpad that deals with this to allow us to be capable of having a sustained presence on the moon? We decided to go for a twofold solution. So in the immediate term, we used temporary deployable pads for early operations. We looked at conventional and innovation solutions, which range from carbon fiber blankets to plume-deployed systems. However, as technology developed, launch vehicles became more readily available and operations increased, we moved towards an ISRU-built pad. What better way to build from the ground up than to use the ground itself as our material? We used 3D printed regolith bricks to create the paving of our pad. However, we also had to be aware of their load-bearing properties to ensure that it could sustain repeated launch and landings. In order to do this, we used various techniques, including post-injected metal reinforcement and fiber-reinforced regolith composite. On top of this, we still have to decide whether we want to use the natural topography of the moon or create an artificial platform. In the lunar South Pole, there are many small craters, and this could potentially present an elegant and cost-effective idea of where to put our space pad. However, this also comes with its own technical challenges, even though the walls of the craters could be used to shield the surroundings. So instead, we decided to go for an engineered planar surface that you can see here. We used artificial berms for in a vortex generator configuration, which essentially limits the exhaust plume from expanding away from our spaceport. It also dissipates the kinetic energy into heat. So this means, in simple terms, we shaped the plume instead of letting the plume shape our port. And finally, even a perfectly built pad doesn't create a spaceport by itself. You need hands on deck before humans arrive and to work alongside them afterwards. In 2024, NASA released a white paper under their Moon to Mars architecture plans that highlighted the mismatching capability for logistics and mobility on the surface of the moon. How do we actually offload our cargo? How do we move around the surface? How do we move away from a singular point to an expandable and scalable spaceport of the future? We decided to tackle this problem with a combination of telerobotics and autonomous systems to prepare the site, offload cargo, and assist EVAs. One thing we often take for granted on Earth is the access to an efficient transport system that can move both cargo and humans. How can we replicate this on the surface of the moon and still take into account the extremely harsh environments that exist? We looked at various systems, comparing payload capacity, adaptability, and cost, and decided on a hybrid solution that would tackle this problem, and we still use in our spaceport today. We used a system for fixed corridors called Float that uses magnetic levitation over a track with electromagnetic drive. This system is lightweight, dust tolerant, and reconfigurable with very little site preparation, as rovers can deploy these tracks themselves. However, you are then bound to these tracks, which doesn't allow for much exploration. To close this gap, we used a swarm of lunar hoppers that enable last mile and exploration capabilities. These are terrain agnostic, but also come with a high fuel cost. And so this technology only became feasible as ISRU technologies also developed. With the foundation set, a safe site, a durable pad, and mobility that scales, the next chapter is power and communications.
From the very beginning of our spaceport, we faced a major challenge. How do we go about designing a sustainable lunar spaceport when minimal lunar communication infrastructure exists? There are no satellite constellations overhead yet. And communication with the Earth is intermittent at best. Yet even with these challenges, a lunar spaceport requires 3 critical capabilities: reliable power, continuous communication, and precise navigation. For this, we proposed a solution designed to work from day one, but be able to scale and build into a permanent lunar positioning, navigation, and communication infrastructure. At the center of it all is the Lunar Surface Structure, or the LSS. This is a fixed, shielded hub designed to survive radiation and temperature extremes that exist on the lunar surface. Within it is an atomic clock, which is responsible for providing a reference for timing and navigation for the entire system. Having a local atomic clock on the moon means faster trajectory calculations are possible, along with more precise navigation. It also provides synchronized operation to the entire lunar surface. When Earth is available to be contacted from the South Pole, the lunar surface structure can synchronize with terrestrial time standards. However, during the frequent times where Earth contact is unavailable, the LSS is still able to maintain timing and synchronization across the entire network. Now, outside of the LSS, we have our multi-purpose reusable towers, or the MPRTs for short. These are placed high on ridges where sunlight is abundant, and they pull triple duty, generating solar power, beaming that power to where it's necessary, and sending and receiving signals for power and communications. Now, this design drew inspiration from Honeybee Robotics' Lunar Saber concept. And lastly, we introduced mobility in the form of mobile mesh nodes, rovers that could act as communication and navigation points. These shifted around the landscape, filling in blind spots and extending mission coverage to new sites. Together, the rovers, the hub, the towers all acted as a network of self-calibrating pseudolite arrays, meaning instead of needing a detailed pre-survey of the moon or constant surveillance from satellites, each node, or pseudolite, could determine its own position relative to another using bidirectional ranging techniques, effectively creating a system that changed as its conditions changed. However, adaptability and flexibility was never just about location. It was also about communication. And this is where our towers come in. Our towers can dynamically shift between Wi-Fi, UHF S-band, and 4G, 5G communications. This flexibility was key since a rover in a crater may need low-frequency, long-range links where the base itself may require high bandwidth data rates. However, communication was only half the challenge. The rest was power. So each tower, using its solar powers, generated between 10 to 100 kilowatts of energy. Our power distribution system ensured survivability and flexibility by incorporating autonomy and robotics as to not rely on human oversight. Our power distribution system also had to distribute that power to operations that required it. Now, the most efficient way to distribute power short-term distances is cables, as it reduces losses caused by high voltage conversion rates. However, not everything that needs power is going to be within a short distance or a fixed distance of these towers. And this is where optical wireless power transmission comes in, or OWPT for short. Using OWPT, we can effectively beam power generated from the towers to remote or mobile assets that don't have access to their own power generation sources. And this asset is particularly valuable when we're referring to high energy intensive operations, such as hydrogen extraction in permanently shadowed regions on the moon. And this is where the true scale of our power system comes in, because it was never just about keeping the lights on in our habitat. It was about enabling heavy industry on the moon itself. Let's look at hydrogen production as an example. To have a sustainable spaceport, we require our own fuel. But having rocket-ready hydrogen fuel is highly energy intensive. So here's some numbers, just so you get an idea. To extract about 1 kilogram of hydrogen, it requires 50 kilowatt hours of power once inefficiencies are taken into account. Once we have that hydrogen, we have to liquefy it, which takes another 6 to 13 kilowatt hours. Now, liquid hydrogen is notoriously difficult to handle and store. So to fix this problem, we converted it into ammonia. But once we needed that hydrogen back into its pure form, we had to break it back out, costing us another 2 to 3 kilowatt hours. Those numbers that I showed just goes to show how critical a steady high power supply is. Now, this system, although it was designed to work from day one with minimal communication infrastructure, it was never meant to stand alone in the long term. It was meant to integrate and to become a part of something larger. And that larger something is Lunar Net, NASA's planned network of networks for the moon. Think of it as internet for the lunar surface. By making our tower, our hubs, and our rovers Lunar Net compatible, we made sure that they didn't just act as local network for the South Pole Spaceport. They became service providers for the entire lunar network. So here's the vision. A single hub, a handful of towers, and a few rovers laid the foundation. From there, we grew outward. The network expanded. We powered mining sites, we guided landers, and we kept astronauts connected. Power where it's needed, navigation that works everywhere, and communication that never fails. This is a system that made the first lunar spaceport possible, and it's the one that will continue to support the lunar economy for years to come.
When we initially set out to build the first lunar spaceport, the engineering problems were the ones everyone focused on. Could we land safely? Could we survive in such a harsh environment? Could we generate enough power? And yes, we solved those problems. But what became clear was that the harder questions weren't about the steel and the concrete. They were about the people. Who gets to launch first? Who pays for the upkeep? What happens when you have two companies who want to use the same landing slot? We couldn't just import Earth's patchwork of laws and hope for the best. On the moon, every litre of water and every hour of sunlight is crucial. And so we needed a governance system as carefully designed as the rockets themselves. So we began with a phased approach. At the start, the first lunar spaceport was financed and operated by government. Think of it like the early days of aviation. However, from the very beginning, we knew it couldn't stay government-led forever. As lunar activity grows, innovation and efficiency had to take the lead. That's when we shifted into the second phase, commercial operation. Ownership and management transitioned to private entities, and revenue streams diversified to not only include landing fees, but fuel depots and tourist services, which ensured not just survival, but profitability. Of course, all of this needed rules. And so 3 key institutions became the backbone of the lunar society that we have today. Firstly, the Lunar Council, a multinational forum that brings together nations, companies, and individuals in order to agree common standards and arbitrate disputes before they escalate. Secondly, we have the lunar credit system. Instead of land ownership, which is outlawed by international treaties, we have credits. You earn credits by contributing, whether that's building infrastructure, providing resources, or providing services. These credits give you access and priority, and they are tradable. This creates a fair, incentive-driven economy. And thirdly, the Lunar Tribunal. This was set up due to conflicts being inevitable. The focus of the tribunal is to resolve disputes as quickly and transparently as possible, guided by both international law and lunar precedents. Disputes on the moon need to be resolved quickly, as operations simply cannot wait. Together, these 3 systems turned what could have been a frontier free-for-all into the functioning society that we have today. Looking back, the brilliance wasn't in any one single innovation. It was in bringing them together. This allowed industries to link seamlessly between the Earth and the Moon into a single value chain. But more than that, it gave us a model, a way of building societies beyond Earth that was fair, sustainable, and cooperative. We didn't just build a spaceport, we built a framework for how humanity could live, work, and thrive. However, establishing fair laws and a credit system was only half the story. The real challenge came when we had to go from these foundations into building the actual physical spaceport on the lunar surface. Building the spaceport was far more than a matter of ambition. It was a complex and expensive endeavor. The largest costs came from 2 key factors: transportation and delays. Getting materials from the Earth to the Moon was extremely expensive. And even though reusable rockets like Starship brought down the costs, they still remain significant. Every day of delay also had real economic consequences. Scientific experiments were pushed back, commercial opportunities missed, and private investment delayed. When considering the Launchpad, for example, we considered 8 different construction methods under different transport and delay scenarios, and the results were clear. Total costs were extremely sensitive to these 2 factors. Faster construction methods reduced delay costs, but required heavier, more complex equipment, which therefore were more expensive to transport. In the end, the method we chose was brick paving the landing pads. It was slower, but it offered modularity, easier repair, and scalability, qualities we knew would be key to making this last for generations. We accepted the higher short-term delay costs in order to build something that would be sustainable for the long term. The strategy to make the spaceport a reality also depended on financing. Short-term returns were uncertain, and break-even seemed decades away without supplementary revenue streams like in-situ resource utilization, in-space manufacturing, and lunar tourism. Lessons from Earth were instructive. Spaceport America, for example, had cost $220 million to construct, and yet was only bringing in $7 million annually. Launch revenues alone simply couldn't carry such an investment. The solution was a state-led development model. Governments financed the initial investment, reducing risk and attracting private partners who provided manufacturing, services, and co-investment. Over time, this evolved into public-private partnerships, shifting from government-led construction to commercial-led operation. Revenue strategies followed similar logic, with launches being just the beginning. Logistics, tourism, resource extraction, and in-space manufacturing created multiple revenue streams, securing long-term sustainability. Through careful cost management, strategic public-private partnerships, and diversified revenue planning, what had once been a high-risk, government-led project became the thriving, commercially viable hub you see today. The Moon's first spaceport was no longer just a dream, but a functional, operational spaceport, which expanded and a sustainable gateway to humanity's presence beyond Earth. This established the foundation for us to go from a rudimentary spaceport into the fully functioning one we see today. Now, let's explore this further.
I want you all to appreciate where we are right now, with a settlement of over 1,000 people nearby and hosting over 5 launches and 5 landings per day. You're surrounded by multiple launch pads, not just one anymore. We have so many satellites for endless communication. Think about the rover that you drove in here today with, or about the 3D interior design that you're immersed in right now. So now let's take a tour of the spaceport as it stands today and see every section.
We're all gathered here today at the Lunar Spaceport, and you might be wondering, how did we build a lasting presence on the moon? And it wasn't anymore about just landing missions, but it was actually about creating a sustainable ecosystem that could thrive over time. And that meant a shift of paradigm. So now we're not anymore connecting individual technologies and few technologies, but we're actually having the ability to connect various technologies and to evolve them over time as we live here. So let's understand how each system is implemented and how it intertwines. And to understand that, first of all, we need to understand the role of the spaceport. And the spaceport, for us, it is an anchor of the system.
And it's more than just infrastructure. It is the central hub that keeps a sustained presence alive and functional. And if we're going to explore the systems that compose the spaceport, we're going to start now with the communications one. And so robust communications on and around the moon are essential to the success of any sustainable lunar presence, because it is what connects all the nodes of our complex subsystems. And we have first our communication subsystem, and we're going to explore each part of it as the main, the highlights of how it works. So when we launch our communication system, we have to think about, first of all, security of the data that we are transmitting. So we use cybersecurity protocols. Next, we want to establish low latency links, so we have data fast through the most advanced protocols as well. We need to connect crew and spacecraft so we can start receiving telemetry and data from them. We synchronize with navigation systems, GNSS systems, and complementary systems that we have to support navigation. And we enable AI-driven autonomous incident response so that we don't rely on humans to carry out incident responses. And now if we go to Earth, we are also receiving telemetry streams from the lunar operations, and we are receiving other types of data, such as scientific data of everything that we are developing on the moon. And finally, with this data, we can run predictive digital twin simulations. They can be run on Earth, and we can have an overview of what's happening on the moon and plan ahead for future missions. And those are the systems that allow communications for sustained lunar operations. And how did we make it happen? So as we've seen before throughout this presentation, the communication systems are built on resilient multi-layered networks designed to provide uninterrupted connectivity. And constellations of satellites in lunar orbit ensure this continuous coverage, while strategically positioned relay satellites can also extend the links to areas of the moon that are not as easy to access, for instance, the lunar far side and polar regions. And to enable the communication links themselves, we have two types of technologies. One is the already traditional radio frequency technology, which has broader beam omnidirectional coverage and weather resiliency. But we also have high capacity optical links for when we want to send data, such as scientific data, heavy imagery. And it doesn't have the same broad coverage, but it does allow for ultra high data rate transmissions and throughput. And thanks to those elements, we can have international, governmental, and commercial partners cooperating and coordinating effectively. And this is while real-time data sharing and redundancy strengthens the autonomy and provide rapid response in critical situations as well. And in short, communications form the backbone for safety, collaboration, and progress on the moon. And now we are going to also see about transportation, which is the lifeline of the lunar presence, because it links the spaceport with all the other sites on the surface, in orbit, and also along the Earth-Moon corridor. And transportation allows the reliable movement of crew, cargo, and resources, essential not only for astronaut and mission activities and transporting supplies, but also for other larger scale operations, such as propellant transfer and refueling. And as we speak about transportation, some of the methods that we have and that we have seen before, they are diverse integrated systems that combine rovers, maglev trains, rockets, and advanced launch concepts such as centrifugal launches. And to keep this network operating continuously, we have fueling and charging stations that are strategically deployed across the service, but also in orbit, supported by autonomous maintenance to sustain equipment health. So we have autonomously our equipment being able to recuperate itself. And so, as I mentioned, transportation extends beyond the surface through orbital refueling capabilities so that we can have sustainable practice that allows spacecraft to extend its operational lifespan. And navigation adds on to transportation by enabling critical functions such as spacecraft rendezvous, pinpoint landings, crew mobility, and vehicle operations. So let's explore this further as well. In this stage, lunar navigation is built on precise and resilient positioning and timing systems that ensure accuracy across the surface and in orbit through dedicated lunar GNSS constellations providing continuous coverage. And in addition, high-precision quantum inertial sensors, which is an advanced technology that we use now to complement satellite-based navigations, allows vehicles and equipment to maintain accurate positioning even if we lose the signals from the GNSS constellations that we have. And navigation also involves towards autonomous operations, and we use artificial intelligence to coordinate traffic, correct trajectory, and avoid hazards in real time through our predictive modelings in real time. And so by transmitting back telemetry and data, as we mentioned before, we have digital twins on Earth, and we can get all this data and build a simulation of navigation on Earth so we can plan ahead other missions on the moon. And when the moon has become a busy hub of spacecraft, satellites, and rovers, we decided to go for an approach of traffic management to be our invisible hand, keeping everything move safely and efficiently. And what is traffic management for us? We call it cislunar traffic management, and it is this lunar equivalent of the Earth's traffic management, a framework composed of very similar analogous components and domains, and that coordinates activity across the moon's land, orbit, and cislunar space. And so just as the Earth's equivalent cislunar traffic services has similar capabilities, however transposed to our needs in space. So for cislunar traffic services, we track spacecraft this time, we deconflict trajectories of spacecraft, we manage docking and landing operations, especially when we have multiple landings at the same time, and we use AI systems and planning to prevent collisions as well. With cislunar space management, that's where we define the operational zones of spacecraft. We assign access rights together with all the international entities that are part of space at this point, and safety corridors as well for spacecraft to go through. And finally, with the third big domain, which is cislunar traffic flow management, it's the more dynamic domain where we coordinate launch windows, orbital transfers, and refueling logistics for optimized resource use. And so communications, navigation, and transportation form the backbone of a sustained lunar presence. And within the cislunar traffic management framework, the systems provide essential support for crew safety, efficient operations, and ultimately mission success. Running these systems continuously requires energy levels that we never had needed before on the moon, because we now are considering power requirements of technologies that are far more advanced, such as high bandwidth communications, autonomous operations, and quantum navigation systems. And so not only is the energy demand high, it also varies according to each mission, its schedule, and the associated infrastructure that we'll need at times, while backup systems also further increased our needs for energy. So meeting those needs is critical for maintaining operations, making energy the central bridge that enables the potential of our spaceport.
To have a long-term, sustainable, and thriving lunar spaceport, there are some key foundational cornerstones which must be achieved. One of these is energy. Without energy, nothing happens. So if we want to have a spaceport that stays alive, this is the problem we need to solve. Luckily, we have solved this issue. Energy is split into two main parts. There are the energy requirements and the energy usage. Now, these may sound similar, but they are different. Now, before we dive in, there are a few details you need to know about our spaceport. As mentioned previously, there is also a lunar habitat of 1,000 people, Our spaceport supports this, but is distinctly separate and has a capacity for 200 people, and 200 people currently live there. However, it is designed for 300 people for emergency situations. The values you'll see are for this 300-person maximum. Now, the power forecast, or the power requirement. As you can see, the spaceport is in 7 different subsections. The first one of these is habitation. Oxygen generation, life support systems, habitation modules. Anything designed to keep people alive on the moon goes within this subsystem. As you can see, it requires 960 kilowatts of power. The next one is mission control and communications. As the name suggests, this is all about communications. However, not just from spaceport to rocket. It is rocket to rocket, spaceport to spaceport, moon to Earth and Earth to moon. And as we learned, these are very important subsystems, and they require over 150 kilowatts of power. Propellant. If you are landing and launching 10 rockets a day, you need to be able to store 10 launches worth of fuel. This fuel is liquid oxygen and liquid hydrogen. Specifically, 50 tons of it needs to be stored. Now, these fuels need to be kept in liquid form. And to do this, you need cryogenic temperatures, and you need refrigeration for this. This requires 2.4 kilowatts of power. Now, 413 is larger than 2.4, obviously, and this is because we're not just storing the fuel. The fuel needs to be transported from storage into the rockets. Each rocket requires 5 tons of fuel, and they are refueled in 15 minutes. To get the desired volumetric flow rate, we need an extra 411 kilowatts of power. Now, maintenance and fabrication. With so many rocket launches per day and so much cargo coming in and out, you need somewhere to store this cargo, and you need somewhere to do routine maintenance to make sure everything keeps running smoothly. This section requires 733 kilowatts. Now, the next one, which also goes with this, but is also separate, are pad operations. This is everything that is specifically with the launch pad and its auxiliary systems. This requires 933 kilowatts of power, one of the more power-hungry sections of our spaceport. Now, the next one, 10 kilowatts of power. It may be much smaller, but it's no less important. This is the mobility. This is amongst and to the different launch pads. We have 5 launch pads. Each launch pad has 4 rovers attached to it, and each rover requires 0.5 kilowatts of energy. This gives us the 10 kilowatts of power that we have. And last but not least is the launch suppression system, or the rocket launch suppression system, or RLSS. This is also a vital part of our launch pad. This makes it so the rockets can actually launch and survive. If the rockets or the launch pads destroy themselves during launch, this is not a good thing. Now, as you can see, our total power usage is 4,500 kilowatts, or 4.5 megawatts. This is a very large number. However, it is not representative of the actual power usage. This is the peak power. This is the actual power usage. As you can see, there are high points and low points, peaks and troughs, consistencies and inconsistencies. And this gives us an average closer to about 3,000 kilowatts rather than the projected 4,500. Now, we know where the power is going, but how do we store this power? We have a 3-pronged approach. We will be using flywheels, conventional batteries, and fuel cells. Flywheels will account for 60% of our energy storage. This is because they are very good at ironing out inconsistencies. With the energy generation, if there are frequency issues, spikes in power, flywheels are very good at mitigating this and providing a constant smooth power to our spaceport system. The remaining 40% will be handled by the batteries. These are solid-state lithium-ion batteries. They were chosen for a number of reasons. One, they have a very wide operating temperature. This is obviously very good for the moon. They have a high energy density, and they are rechargeable. This is most important because they are active for 17.5 hours each day or each 24-hour period. So they'll be cycling, they'll be drained and refueled, so they need to be rechargeable. Fuel cells are also suitable for energy storage. However, they serve a different purpose. They are the emergency backup system. This is because they have a very desirable trait. They have a rapid load response. This means if the system goes down, this emergency system can kick in very quickly. And due to their high operational lifetime, they are very good for this purpose. Now, power generation. We know what uses the power, we know where we're going to keep it, but where do we get it from? Again, we have a three-pronged approach. We use small modular nuclear reactors, space solar power systems, and thermal solar power. We chose these three so that we don't have a reliance on a single system. So if this single system breaks down, bad things happen. Now, small modular nuclear reactors, as the name suggests, they are very similar to regular nuclear reactors. They use the same operation methods. However, they are smaller, easier to assemble, and now they are capable of achieving the same output as the traditional nuclear reactors did 50 years ago. The space solar power systems. This takes solar energy and converts it into optical and microwave energy. This allows it to be beamed across the moon and across the spaceport to where it is required the most. And the thermal solar power. This is similar to traditional solar panels, which use photovoltaics, but instead of turning sunlight directly into electricity, this system concentrates the sunlight to generate a lot of heat. This heat then boils a liquid, which in turn spins a turbine, creating energy that we so need. Now, these systems were chosen due to some key characteristics, which makes them very valuable for the lunar surface. One is their dust robustness. These systems can work in very dusty environments, and the moon is a very dusty environment. Another key desirable is the scalability. If we want to build more spaceports, make our current spaceports bigger, we need to have power systems which are scalable. If we use the same power systems, we know that they work, we know that they work for our system, and we know that they are reliable. So for these reasons, these three generation methods were chosen. Now, I mentioned there are key foundational cornerstones. Energy is one of them, but it's not the only one. We know how the spaceport operates, but how about the people actually operating it?
What makes this place come alive isn't just the skeleton of steel and regolith, but the beating heart of the system, which is the workers themselves. The workers are both the foundation and the vulnerability of the spaceport. And it's important to not just think about the hardware, but also about the health, resilience, and the well-being of people that make it run. That's where our design came in. Let's start with the air you're breathing right now. On the International Space Station, astronauts consistently had to deal with elevated CO2 levels, strange odors, and fine particulates. This was uncomfortable. It affected their cognition, mood, and sleep. Now imagine amplifying that challenge. Instead of having 6 astronauts, we have a lunar workforce of over 200 people. Poor air quality chips away at health and can affect morale, productivity, and long-term success of the missions. Our approach was a digital twin-enabled environmental control and life support system. So instead of simply reacting to a situation as the problems come up, we can predict what is going to happen months in advance. By continuously monitoring, we can be able to predict, for example, the level of carbon dioxide elevating in about 6 months. And instead of waiting to deal with it, when it becomes a hazard, we can address it now. This kind of predictive autonomous maintenance has never been done before for the life support systems, and it was key to making the lunar spaceport safe and sustainable for a workforce of this size. But sustaining workers isn't just about their physical health. The psychological toll of living and working in an isolated, extreme environment is just as important. On Earth, other isolated workers, like coal miners, show rates of depression and anxiety 37% and 38% higher than the general population. Imagine yourself working at our lunar spaceport, surrounded by multiple launches a day that are pretty dangerous. But not only that, but you're also days away from any direct support from Earth. And on top of it all you see around when you're walking is cool steel walls. That would make me pretty uncomfortable. But stress isn't just uncomfortable. Chronic stress can actually affect the structure of your brain, harming cognition, decision-making, and emotional regulation. This means morale, productivity, and even safety are directly tied to how we address the psychological environment here at the spaceport. But there's also the social aspect. Maintaining cohesion and unity in any workforce is important, but even more so on the moon, because even a small conflict can lead to catastrophic consequences. And maintaining cohesion is mission critical, and you're only as strong as your weakest link. So it's important for us to create a healthy and happy culture here. And that's why building psychological resilience into the architecture was just as important as building the launch pads for us. So how did we do this? Everything for us was about senses. It was about bringing a piece of Earth to the moon to make living here as comfortable and warm as possible. So let's take a walk. We're going to start here in our cafe area. Imagine workers having a nice meal with fresh food, maybe fish or fruit, surrounded by plants and a real-time screen that actually simulates a window. So you feel like you're part of an environment that is living and human. But we also have other facilities, like the gym, that keeps the mind and the body strong, especially in low gravity. A library, and we also have 3D immersion rooms that can show you earthscapes to ease homesickness. But when you also need solitude, which people do, you can retreat into privacy capsules where you can meditate, relax, or just sleep. But everyone's favorite part is the botanic garden, where there is actual plants, trees, and vegetation growing under artificial sunlight. As you walk around, there's soundscapes, like birdsong in the morning or a subtle wind in the evening. The entire environment of the spaceport is covered by artificial circadian lighting to also promote healthy sleep cycles. We also use different textures to invite touch, like soft couches or warm wood-like panels. Even scent is used intentionally. Right now, if you take a deep breath, you can smell green, humid, alive. At the coffee lounge, you could have also smelled coffee. Every detail here is tuned to say you're not part of a sterile dome. You're actually part of a living human world, even here on the moon. In the end, building a lunar spaceport wasn't just an engineering challenge. It was a cultural one. The sustainability of this place depended on the workers just as much as it did on power grids and the rocket ships. To get this, we acknowledge that we're not building infrastructure. We are also building one of the first blueprints of the truly sustainable human presence beyond Earth, a spaceport that not only welcomes its workers, but tourists from Earth.
When we first began thinking about the future of lunar spaceports, we realized it could never just be a launch pad. It had to truly thrive, it had to be a place that people could experience, which is why we put habitation and human-centric design at the center of our focus, especially when it came to lunar tourism. We didn't stop at the idea of a visitor stepping onto the lunar surface and taking a selfie with the Earth in the background. Instead, we built a ladder of offerings with different tiers of services to cater for every dream, ambition, and budget. For some, it's as simple as a live virtual reality moonwalk streamed straight to their living rooms on Earth. For others, it's transit and excursion packages that take them onto the lunar surface and maybe even to explore a lava tube or two. And for the most adventurous, it's the chance to spend time in a wellness-focused lunar habitat. But lunar tourism is not just about indulgence. From the beginning, we recognized it as a cornerstone for economic sustainability for the spaceport itself. Tourism brings in investment, creates recurring revenue, and creates the foundations for future long-term growth. To make this work, we built a model based on partnerships, governments provide the shared infrastructure and common standards, while private institutions can focus on building experiences for the consumers. This balance allows innovation and luxury to flourish, while ensuring the spaceport remains open, accessible, and financially viable. In this way, tourism is more than just an add-on. It is an engine that sustains the spaceport, ties the lunar economy into Earth-based value chains, and transforms the moon from an outpost into a destination. But of course, experiences like lunar tourism, and indeed every aspect of life and commerce on the moon, depend on more than just rockets and habitats. They rely on trust. Trust that resources will be shared, that contracts will be honoured, and that every participant, whether a tourist, company, or nation, has a voice in how the society operates. On the moon, where every drop of water and every watt of power counts, that trust can't be left to fragile democracy. It has to be built into the system itself. This is why blockchain technology has been proposed as the potential foundation for future lunar governance, economy, and society. Blockchain is a digital ledger that records every transaction transparently and permanently. Tokenization turns rights, resources, or assets like water, energy, or voting power into digital tokens on that ledger. These tokens can track ownership and access automatically, creating a system where trust is embedded in the rules themselves, allowing a community, even on the moon, to operate fairly and efficiently. Like many emerging technologies on Earth, blockchain was once dismissed as a speculative tool. But given the complexity of lunar life, the idea is gaining traction. Governance tokens can give residents a voice in shaping society, while utility tokens connect people directly to the essentials, such as a litre of purified water, a kilowatt of stored solar power, or an hour in a rover for exploration or transport. Smart contracts automate agreements and operations, from commercial trade to regulatory to safety regulations, reducing the burden of manual oversight. The potential is enormous, but so are the challenges. Token allocation must be fair to avoid hoarding and monopolization. Oracles, which are the sensors linking physical assets to the blockchain, must be reliable and secure. Privacy and equality must be safeguarded, ensuring the system does not concentrate power or erode individuals' freedoms. Lessons from science fiction remind us of what can happen when algorithms and automation dominate without safeguards. The vision is clear: a lunar society where transparency, accountability, and efficiency are built into the very fabric of governance. Blockchain may not yet be operational, but serious planning and experimentation are underway. If implemented thoughtfully, it could ensure that the moon remains not only sustainable, but also inclusive, democratic, and resilient. A model for future space settlements, and perhaps even for Earth itself.
As our tour comes to a close, we hope you can see the journey we've taken together, starting at the first daring steps, the challenges of dust, power, and law. There we walk through the rise of governance, ingenuity of power and mobility, and the human-centered designs that led to turning survival into sustainability. Now here we are, standing in a living, breathing lunar spaceport. What once only existed as bold imagination is now alive with workers, technology, and culture. It's more than history, more than infrastructure. It's living proof of what humanity can do when we combine vision, persistence, and cooperation. The moon is no longer a place that we landed on. It's a place we work at, we live in, we visit, and we can thrive in. And this spaceport is only the beginning of what's to come. Thank you so much for joining us on our tour today. I also want to give a big thank you to everybody that made this happen. Everyone was amazing superstars, and they've killed it all along the way. But I also want to give another special thank you to our graphics team, because everything you saw today was made by them. No AI, every single drawing that you saw, they worked tirelessly till 3 a.m. So I just want to also give them that credit. But now we will take any questions. Thank you.
So, does somebody have any questions? Justin?
Guess I'll just get the mic. Great presentation, guys. I thought it was awesome. Now, my question has to do with the power generation in the long term. So when determining how much power you needed for your lunar base, I noticed that you had the maximums of each system that was required. Did you consider the nominal operations and what would be needed for that, or the maximum when everything was at its maximum? Because I would assume that would be a rare event.
So yes, so first of all, that table that you saw, yes, was the maximum amount, but then we made a power schedule, which if that was a graph showing the 24-hour working day, theoretical working day of the spaceport, and how much power at each event would be used during the day. For example, when the spaceport is shut, we won't be really using the launch pads. When there's nothing launching, there's no launch suppression system that's working, which is why the graph is not a constant. But there is an average nominal power. I'm not sure if it was in the presentation itself, but I believe it's around 3.5 megawatts for on average.
We have one question online, Remco.
Yes, I hope you can hear me, that my sound is working.
Yes.
Very cool. Thank you very much for that presentation. That was a very extensive walkthrough of what we can expect in, well, a few decades. But there's one thing that I kind of noticed that contrasts a little bit with the reality as we see it today, especially this ideal picture that you paint of global collaboration on the moon, where we are not necessarily globally collaborating here on Earth. And what we usually see is that what happens on Earth is replicated in other places where we go to. So you talk about your research, including both the ILRS and the Artemis project, but I see mostly a very Western point of view here, including your choice of examples for the infrastructure like Starship, and in the report you mentioned Lunar Net and other things. How do you foresee the Artemis ILRS collaboration, so the collaboration between mostly the Western view of things and the Chinese developments as we see them becoming more competitive here on Earth, while the picture that you paint is one of the ideal global collaboration? How should I see that? How does that reflect in your vision on this lunar habitat?
I think I somewhat understand your question. I mean, in terms of jurisdiction, ownership, extraction regarding resources and utilization of those resources. Yes, our starting point was the early Artemis missions. So like you said, very Western based. One of the, at the heart of innovation and trying to, I suppose, globalize the efforts. One thing that the group considered was when you have the for example, the Outer Space Treaty and at the heart of that, stating it's the moon is for all of mankind or all of humankind, and no property should be owned by any nations. And then we see also those early Artemis Accord missions where national laws have been enacted, and now you have legislation in place for not only resource use, but resource ownership and resource sales. So the heart of our innovation, and this is what led into the Lunar Credit System, the Lunar Council, and then the Lunar Tribunal, was the various stakeholders. So at the beginning, we talked about the government nations being the main contributors, but as lunar activity increases, price of transportation decreases for reaching the moon and establishing infrastructure. The heart of that was that if you're contributing to lunar development, then you would earn these credits. And keeping it in-house, keeping it on the moon, was one way that we all thought would be a fair way to make it accessible for equitable and equality reasons, that any nation or any companies from around the world could take part in. So I believe that answers at least one part of the question where you're getting at.
Okay,
Sure,
thank you for that. I'll let others ask questions.
All right, thank you.
Yeah, one question here. Perfect.
So I saw that there were 3 power systems, like generation methods: small modular, space solar, and thermal solar. When I think about something that's sustainable for creating a spaceport there, how were these 3 selected? 3 different systems. I understand needing one for backup, but now we're talking about development and maintenance costs.
So it's important to have 3 fundamentally separate systems for a spaceport, obviously for the reliability. So you wanted at least 3, and all of them to operate on very different levels from each other, i.e. they would require different maintenance schedules, different, I guess, requirements for running. one of the designs that we put forward is that the spaceports, the habitations, and even a limited run of actually launching can be sustained by even one system on its own. So that was part of it. So we can lose systems and still run the spaceport to a capacity. Obviously, we need all three to run. Also, two of the power systems were chosen because they have completely constant power generation. So because of course the spaceport will need to function during the lunar night as well. If we're talking about 1,000 people, it's possible that we will need to launch and we will need to have power during the lunar night. So it's not enough to just use, say, ground-based solar, where we have to have an immense amount of batteries to store enough power and also enough solar panels to generate that power over the daytime.
If there are no questions in South Korea, then let's go back online. I think Demetra was first.
Good morning, good afternoon. Thank you very much for the very informative presentation. I have a question concerning the environment. Here on the Earth, when it comes to airports and to spaceports, we are very much concerned about the environment surrounding a port, waste management, especially when something becomes more and more popular, emissions for takeoffs and launches. How do you incorporate, if you incorporate these concerns in your lunar spaceport?
Okay, so our short-term and long-term proposal were based over the three principles of sustainability: economical, environmental, and social sustainability. But we also try to focus on the 17 goals of sustainability that we have here on Earth. So we try to target specific proposals for each of them. And we have right now, like, on our report, we have like a specific proposals for each of the goals that we have here. So we target them all, not only in an environmental way, but also social and economically.
Thank you.
Just to add to that as well, one thing that we did, especially in short term with energy generation and storage, was to particularly look at how that affects the environment. So one thing that we did was go for hydrogen as our rocket fuel. There are many options that we could have had, but having something that has no carbon in it and also storing it in ammonia with also no carbon is under that impression of making sure that we're making the most, the least impact on the environment as much as possible. So that goes for a lot of the things we did in the short term, but yeah, I don't know if anyone else wants to add.
Again, in short term, for example, in terms of infrastructure, those artificial berms or natural berms, both the concepts, they are intended to avoid the spoil also of the landscape around it. So by containing the rocket exhaust plumes and avoiding the dust dispersal, you're also protecting the environment around it. I think it gets to your point as well.
Thank you.
Another one.
Last thing to add with long-term power generation, one of the reasons why we actually chose our power storage to be mostly flywheels was also that batteries themselves, of course, deteriorate after cycles, and disposing of batteries is a difficult thing to do. So one of the things about flywheels is because it's a mechanical energy storage, they don't have the same deterioration, but also they can be made completely in ISRU because you can get the mass from the lunar surface to put into the flywheels. So they're actually a lot less damaging over the long term to dispose of and to replace.
Thank you all so much.
Another impact that we use in our report on the long term is the implications of all the emissions from the spaceport on the health of people inside the lunar base. So we put some requirement on the air quality to make sure everyone will not be damaged by all the emissions.
Have a look here in Ansan, no questions. Okay, I think next up online would be Maurizio. Go ahead, please.
Hi, everybody.
First of all, congratulations for the excellent narrative, for the charming and intriguing slides, which are really presenting a very visionary situation on the moon. I have two questions. I try to keep very short. Please allow me to raise both, one after the other. The first one is concerning whether you have done quantitative analysis and assessment of your vision. Just to bring few examples. You are mentioning electrostatic field to repel the lunar dust. Did you run an analysis whether is EMC compatible with the operations, running the operations? A second point, you are mentioning the lunar bases will be run by 200 persons to support 5 launch days. How many persons are there at KSC in Florida, for instance, or Baikonur in Kazakhstan to run much, much less number of launches per year? Or you make reference to a future cislunar traffic management along the line of what's going on Earth, but actually space traffic management currently is not there on Earth because it's in hot topics of strong disagreement, unfortunately, or lack of agreement between nations. They are on the engineering side. My second question, very short, is on a different side. You mentioned Lunar Council, Lunar Credit, Lunar Tribunal. I guess you are missing lunar law enforcement, policemen or similar, to have a total independent new country. Is this what you have in mind? That's my two questions. Thank you.
Thank you very much for your question. Regarding the first one, in terms of quantitative analysis, we pretty much followed what was the state of the art and what was most applicable, what we found most credible for our solution that fulfilled best our vision, and not so much in terms of, it's definitely something that should be looked into, but it wasn't possible for us to pursue to that depth. I don't know if someone wants to add something to this. Then
yes, thank you. In regards to the total sustainment of the moon outside of the Earth, that wasn't exactly our vision. We do recognize the interdependency of that. Within the report we drafted, we did talk about lunar safety regulations, safety committees that would support investigations with the Lunar Tribunal. As you can see, the transition from when our first spaceport began to when you get up to the levels of people there and tourism getting involved, that level of construction obviously brings safety concerns, the need for different looks of regulation. In terms of police enforcement, we haven't got there yet. We still see some interdependence with the Earth, the collaboration there. That may be a long-term idea for us. But again, our vision was keeping the stakeholders, meaning the council, the nations and individuals and companies that contribute to lunar development, to keep them in charge. So that might be something to look at in the future. Thank you.
Thank you. Then we have two more questions online. First, Rob.
Yes, good afternoon, all. And first, also from my point, I would only connect to the previous question askers and experts that I want to congratulate you on this accomplishing this very ambitious task and generating these results in a short time. I do have a few questions, but I mean, most of the questions I had written down, they've already been asked. So, but I do want to follow on then another question, and that is that I see a lot of what I would say is you have a very good overview of what elements need to be taken into account for realizing a spaceport, having the individual needs as well as options. What I missed in the presentation a little bit is what is the underlying user needs and use cases for the spaceport itself. What I see is that you mentioned at some point we can on the long term develop 5 launch pads with 10 launches every day. What are the use cases and user needs to necessitate this frequency of launches? What are you going to do? What are you going to support there?
Yeah, thank you for the question. In the report, we went into one of the biggest usages we see in the future for the lunar spaceport, and this is around the point of fuel. As we got into the in the report, on the lunar surface, we will be able to create fuel from the water ice on the poles, and this water ice is going to be converted into the fuel we're going to use for all lunar exploration, but also can be used to get the fuel into cislunar space and support the activities everywhere inside the cislunar area. The thing is that getting into the cislunar space is much easier from the lunar space than from Earth. So we believe that when we will get to the point of having a functioning spaceport, most activities that we will want to do between the Earth and the Moon, or even on Earth orbit, will be produced and sent from the Moon. For example, any refueling missions will come from the Moon because it's much easier to get from the Moon to Earth orbit even. And even if we want to put satellites around the Earth and we can actually create them on the Moon, it will be much more easier and sustainable to create them on the Moon and send them to Earth, as it will be much cheaper and faster to do so.
Okay, thank you.
Thank you. We have one incognito question online as well by Peter. Please go ahead.
Yeah, sorry. Let's say that everybody says that I could raise this the chat. Let's say by raise the hand, but it doesn't seem to be working on my system. But once again, congratulations! It's absolutely fabulous. Knowing, let's say, the very hectic 8 weeks which you had for this in Seoul, and let's say then to have this done within 3 weeks, covering so many different aspects, really top class. Congratulations to the whole team. I read with great interest your 119 pages. So it's a few questions. The picture which you paint seems to be extremely challenging. Let's say so. Did you reflect internally, let's say, when this complete setup, so not only the initial orbital capacity, but let's say, but the full base with 1,000 people, when this could be in place? And a little bit also linked to what Remco has indicated. Let's say that there are many activities now to the moon with ISRO, with ILRS, let's say from the Russian to Chinese, Artemis, ESA. ESA has also got a role to play with Argonauts and with Moonlight. This seems to be a little bit underrepresented. So how does the team see the fact, let's say, that all these individual activities are now taking place, how this can converge into this ideal situation on internationally cooperating? Thank you.
You know, again, I think our starting point was the Artemis missions. So we built off of that in terms of getting everyone involved, maintaining equity in-house stakeholders. So if you're going to be governments, companies, if there is going to be contributions made, then that's when the council gets appointed from, and the credits are earned. So if nations want to get up there and participate, this is the way to do so. And I think one of the challenges we had was envisioning getting the investors on board and having protection for their investments up there. Again, their starting points in the early Artemis missions. We have the treaties stating that you're not going to be able to own the land up there. The land is for all of humankind. But the challenge is when the investors are putting out capital for infrastructure, you obviously want protection for that, and to try and maintain or harmonize that balance for global collaboration and keep the development and exploration going at the beginning anyways. That's when we see the globalization coming together, and then the shift towards tourism as that strengthens the investors, the capital as well. So that was our vision on making an exclusive for everyone, all the nations, investors, and maintaining that harmony of for all humankind. I hope that gets a bit into the question there. Thanks.
And the first question, when we, let's say, what did you reflect on? Let's say when this mass of structures like the antenna and like the mobile towers and this housing capacity for 1,000 people would be ready? Let's say, did you say 2100, 2200? Because you started off by saying that 2075. This seems to be very optimistic. Such a huge infrastructure, or.
Yeah, absolutely. Like when we envisioned the long-term vision, we didn't want to state like some exact year where we are going to be able to be there, because it depends on many factors, including technology and collaboration and many other things that we considered. But we are thinking about, while discussing it, we're thinking about maybe 100 years from now. But that is just some number that we were able to came up, but it depends on many things, as I just said before. And just to add up to the last answer, we think that on the long-term vision, we will have a lot of private collaboration. And just as the NASA states on its Artemis program, while they are taking the lead right now on the development and the technology and everything in the short term, they envision themselves to be more like something very specific on the long term. They just don't want to have control over everything, but they will just want to collaborate in some specific things on the long term. So that's how we envision ourselves also for the long-term vision here. We think at the end, states will be part of this, but the main contributions will be from the private companies.
I'll add to that point as well with that. I think although we've put 2075 on there or so, it's honestly impossible to predict how long exactly the time frame would be, because you have to predict global politics. We could have another space race, a bigger space race than we've ever seen before, and this could be done in 50 years, or everybody could lose interest in space and it'll be done in 200. It's really impossible to predict the future to that level.
Yeah, that's true. And also, let's say the technology, the speed of the technology is very important. I remember being in Guadalajara when Elon Musk showed his chopsticks that the Starship would, and after everybody said, let's say, this is completely surreal. But here it's happening now already a few times. So it's technology can go very fast. No, thank you very much.
If I may just add a little point there to kind of go on in between both of those points, is that there is really a key spectrum of time within our two case studies. So when we looked at the short-term infrastructure development, the primarily goal of that was to drive investment, to drive that logistical chain, to drive the business models. And in doing so, we chose technologies that are earth-based, that are running, that are current, that we know work. And by utilizing those earth-based technologies, we know that we can have a very short-term vision of getting that going, getting that set, and then driving those business models for then the future long-term side. So whilst we do have a long-term goal and short-term technology that's almost ready to use as soon as we put it on the surface of the moon, there is a spectrum in between, which depends on how quickly we drive that business innovation and logistical chain.
Thank you very much. Unfortunately, we don't have the time for any further questions online or on site. With that, thank you for your engaging questions, everyone, and would love to ask the TP Lunar members to the stage. Thank you.
I would just like to thank once again all the participants in the team project for incredible amount of work that came together very quickly at the end. And in fact, I've seen new things that I didn't even see last night. So it's amazing. So congratulations again to the entire team.